This is the measures theory stream, obviously, and we're gonna continue with chapter 2. So last time we finished the main text of measurable functions. So if you guys wonder, like, is this like what is the difficulty? Okay, from now on. So we're deep in the territory of chapter 2, obviously, and chapter 2 actually, in my opinion, is harder than chapter 3 integration. Because once you constructed the measure, things are looking brighter. Because right now, hi, Andre. Thank you so much for joining the stream so soon. Man, you are very dedicated. Just a quick update of where we are right now. Okay, we are at we finished, as I said, the the discussion on measurable functions, at least the main text of it. Um, Doing some content on machine learning. I know I have a lot of requests, Um, so, um, yeah, actually, this is unavoidable, right? Because, I mean, we're doing probability stats and applied math, like machine learning is going to be very relevant to what we do here. But, it's hard to be a full department. like, of, it's hard to be a one-man department, that's what I'm saying. Um, and yeah, of course, machine learning for sure. We will do some, and in particular, probabilistic machine learning. I think that'll be very relevant, right? So, um, and 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 you should have certain expectation of how we do things on the channel, because I'm trying to cover the probability chapter of the book. The probability chapter you see at the very end is at the very end, right? So this one of the I mean, you can call it unfortunate, but I don't consider that to be such a bad thing, because we can actually start with probabilities here once we finish chapter 3. Okay? So Axler's book is written in this way, that it covers the traditional measure theory stuff, um, as well as some functional analysis, and it leaves probability theory at the end as an application. But you don't need to go over everything above to study probability. Of course, there's going to be stuff that's going to be harder than the others. For example, conditional probability. This one's a very difficult one. But you can just say, how do you define expectation and that sort of stuff after finish chapter 3. That's about finite, often, infinitely often. Yes, finite, often, infinite, often. Actually, we discussed that last time, Andre. That's the lim sup and lim inf of events. Finitely often, infinitely often. It's infinitely often and all but finitely often. Okay, so that's the two things I suppose you're talking about. Um, yeah, just to answer a question from Shah, yes, we do at some point have to do some machine learning. Well, don't have to, but I feel like applied math channel is perhaps incomplete if we don't touch machine learning whatsoever. And as you guys probably can tell, I mean, the channel, even though we call it the applied math channel, right? Perhaps it is different from typical applied math, because we do things almost exclusively through derivation. Okay, so if this disappoints you, I'm sorry, but this is just how we do things. Okay, um, there's going to be very little, if any, technology. Okay, this is just my personal preference of doing things, because I mean, nowadays you have lots of packages and stuff. I figure it's kind of a waste of my time to do this kind of thing. What I try to focus on is the fundamentals. This is how I like to approach things. So, and if you want to take a look at how, say, how do you write code from scratch and use packages, that sort of stuff. Perhaps I'll recommend some resources, but I personally, I'll just do derivations. Do derivations, proofs, definitions, examples, manual calculation, that sort of stuff. So it's going to be very minimalistic. Okay, so just as a heads up. Okay, if we do say technology-heavy stuff, technology-heavy subjects such as numerical analysis and machine learning. It's going to be highly mathematical. Of course, it's a math channel. It has to be, right? But you won't see many like computerized examples. All right. So anyway, here, yeah. So of course, we cover measure theory with an aim towards probability, right? With an aim towards probability. But I do wish to perhaps not so single-minded, be not so single-minded. Okay. Horn and Johnson matrix analysis. Yes, this is very good. Perhaps I guess this is very. I mean, it's just encyclopedic book, right? Horn and Johnson on matrix analysis, very encyclopedic book. And I guess under normal circumstances, unless you're taking a course based on it, it's unlikely for you to go through it linearly from cover to cover. So yeah, we'll do some perhaps matrix analysis, numerical linear algebra, that sort of stuff down the road as part of the numerical analysis thing. There are just so many things to cover, man. When it comes to, I just when you do math, you realize how short your life is. It's a melancholic experience, but also a sublime experience. It's like when you stand next to the Niagara Falls. I mean, I live in Canada, so Niagara Falls is the biggest attraction I can think of, but feel free to substitute any kind of natural wonder in your area. Like, you feel you're so small. You see this magnificent scenery. Like, you wonder, how come like this thing came to exist, right? And then you contemplate your own insignificance right next to it. This is how I feel when I do math, basically. So anyway, I think I answered most of the questions, if not all, in chat. So machine learning, yes. Okay. Matrix analysis, yes. No timeline, unfortunately. Sorry. And probability, hell yeah, 100%. So just as a quick update of where we are, okay? Because we're dealing with, in quote, using Axler's word. What does Axler say to students? You are about to immerse yourself in serious mathematics with deep emphasis on obtaining a deep understanding of definition, theorem, proof related to measure, integration, real analysis. Okay, and if you zip through a page in less than an hour, you're probably going too fast. So by Axler's standard, if we manage to read 4 pages, then we're probably doing too fast. Okay, so this is serious stuff. This is serious stuff even for a PhD level math student. So don't feel frustrated. I mean, of course, feel free to feel frustrated, but don't feel discouraged. That's what I'm trying to get to. Don't feel discouraged if you find this is beyond your current level. And worst, don't, and most importantly, do not feel inadequate. You are totally adequate. This is not sorcery. Given enough time and effort, stamina, all those things, you will get through it. Okay. So what only matters at the end of the day is whether you decide this is worth your time, and second, if you actually commit that time. That's just the way it is. Okay. So as I was saying, chapter 2 is actually where a lot of beginners give up. Because actually, chapter 2, measure, is harder than integration. Once measure is defined, integration is easier. This is the upfront cost you pay to get to the integration. Okay. So, and speaking of which, where are we now? Well, we define the sigma algebra and measurable functions, and in particular, Borel sigma algebra and Borel measurable functions. Okay. So, let's just rewind ourselves. Why on earth do we need this? The reason we need sigma algebra and measurable functions is because this unfortunate situation that we cannot extend the notion of length to all subsets of R. Because doing so leads to contradiction. Okay, if we assume the standard axioms in the set theory, okay, in particular the axiom of choice, you will, end up with a contradiction. You cannot do so. Simply, you cannot do so for all subsets of R. Okay, and that's why we need to restrict our definition. We no longer aim to define the notion of length, size, or size for all subsets of R. Instead, we're only going to look at a class of subsets known as sigma algebra. And these are the definition of sigma algebra, which we will probably revisit during the live session, but that's just a restricted class on which we will define our measure. Okay, and the notion of measurable function is really quite straightforward. Okay, the notion of the measurable function is really quite straightforward. So the idea is, first you have something called the Barreau sigma algebra. So the Barreau sigma algebra is the sigma algebra that contains all the nice sets, in particular the open sets. So we want the open sets, and we want a sigma algebra. So your sigma algebra better contain these open sets. That's just Barreau sigma algebra. And then when we talk about measurable function, this is what we mean. So remember, the sigma algebra contains all the sets we wish to define our sizes on. Right? So that we wish to talk about size only for sets in the sigma algebra. And a function from x to r is called as measurable if the preimage is a nice set. That's it. If the preimage, remember the notion of preimage, and by the way, these things, these basic stuff, okay, set theory, preimage, images, all those things, is part of my upcoming live on basics of proof writing, which is tomorrow. So yeah, so you can see if the biggest hurdle when it comes to measure theory is masterful command of just fundamentals of set theory. You know how to manipulate functions and sets, equivalence relation, that sort of thing. You can even make the case that this is even more important than actual knowledge of real analysis. Okay. So there you go, you have a function from x to r, and r, we select a nice set called B. This is a Barreau set, it's a nice set. You want the preimage, which is a subset of big X, is still nice. That's the definition of measurable function. And from that definition, you can prove a bunch of stuff, including an important fact that measurable functions form a vector space. So adding to measurable function gives you another measurable function. Okay. Scalar multiplication also preserves measurability. And also it behaves well under composition, all that sort of nice things. Okay, so that's kind of where we at. We left a few exercises. I mean, we didn't leave, but Axel left a few important exercises last time, because those are in the main text. And so let's try to solve them. So in the main text, there are a few exercises being mentioned here. Okay. So we're in chapter 2, and we're moving things deliberately slowly just to solidify our understanding. Okay. So here, last time we mentioned in the Barreau sigma algebra, where were we? So I managed to solve a few exercises last time. I remember here, measure theory here, measure theory. So I did a few exercises last time. I did 2, I believe. I did 2. So, and by the way, Andre, if you check out last stream, we talk about infinite often. These are lim sup. Infinitely often. That's lim sup of an. An is a sequence of events, and all but finally values is lim inf. Okay. Here, this is a interlude on lim sup lim inf. Okay. This will be extremely useful in probability. But anyway, so last time we did a few, I think I did 2. Yeah, question 3 on Barreau sigma algebra, and exercise 11. So these were mentioned in the text. So I would like to continue on that. So let's first see, just give a quick scan through the main text, which are the exercises mentioned. So in here you have, yes, we covered this one. Exercise 12 is also done. Yeah, exercise 12 is also done. And Cats is going crazy. I don't know why. Here we have exercise 3 to 6. Okay, we did one of them. We did one of them. Actually, we'll do a second one today. We'll do a second one. So 3 to 6, let's circle those. 3 to 6. 3, 4, 5, 6. All right. And what else? What else? Exercise 11. Yeah, we did that last time. See, that's exercise 11. We did that last time. Want to do. I remember there's something else mentioned down here. We're getting close. Yes, exercise 27. This one is important. This one is very important, and it's not easy. Okay, I can tell it's not easy, but it should be doable because it's supposed to mimic the proof of a theorem we had earlier. Okay, which is also important. So we need to repeat that. Right. So just side note, I was doing a Russian stream this morning. Basically, it's called Russian for Mathematician. I recall there was a phrase in Russian called "повторение мать учения." It is called it's like practice is the mother of learning. Повторение мать учения. Andrei, let me know if I said it correctly. So it says practice is sorry, not practice, but repetition. Repetition is the mother of learning. It's like practice makes perfect in English, basically. All right. So Shah says, I've been following the supplement to Mira, kind of like the condensed prerequisite without any formal analysis or proved knowledge. Axler's pedagogy is very tough but rewarding. Well, as far as I can tell, okay, because of the subject matter, Axler's book on measure theory is actually one of the most approachable. Okay, we used Folland in grad school, which is very painful. Okay, well, Axler's text wasn't out yet until I graduated, so that was no use to me. But right now I have the opportunity. So why don't we do some exercises here? Okay, it is through exercises. I mean, I believe I made a video like years ago. I mean, not years ago. I started a channel like 2 years ago, exactly around this time. But about a year and a half ago, I made a video called Exercise Led to the Reader to address this sort of frustration. But all the learning really is in the exercises. I mean, you can read the text not along and whatnot, but this is the real proving ground of your knowledge. Now, it's from the Soviet Union. The saying is from the Soviet Union. Повторение мать учения. Okay. Yeah. So tomorrow morning is going to be a short stream on Russian. Short by this channel standard. All right. We'll continue. Anyway, so let's do question 4. Let's do question 4. So exercise 4. Suppose S is a smallest sigma algebra containing this class of subsets, R to N. R to N, all right. R is in Q, and N is in Z. Prove that S is a collection of real subsets of R. Let's do that. Okay. Kickstart the actual stream with a problem. Best way to start a stream, in my opinion. Most engaging. Okay. Anyway. So prove S is a collection of a real subset. How do we do that? Well, real subsets of R, by definition, is the smallest sigma algebra that contains open sets in R. Let's first recall definition. Collection of Borel sets of R is called Borel sigma algebra. Is called Borel sigma algebra. This is smallest sigma algebra containing open sets in R. Okay. Okay, so what do we know about open sets in R? What do we know about open sets? Well, open sets in R, open sets in R is defined as follows. So A is a subset of R is open, and typically if you use perhaps U, letter U, to denote open set. U is open if for every x in U there exists epsilon greater than 0 such that x minus epsilon, x plus epsilon is contained in U. Okay, the idea is rather straightforward. The idea is every point in U, say x, has a little neighborhood that is contained in U. X plus epsilon, x minus epsilon. The idea is you can never fall. You can say if a point is changed, but if you change the location of a point by a small amount, it would not immediately fall out of the set. There's some sort of wiggle room. So this is U. Okay? The set U. I'm visualizing this as an interval, but it doesn't have to be one. It doesn't have to be one. The thing is, you can pick any point in X, and it's called an interior point. X is an interior point. It's not on the boundary. Okay, that's the intuition. So open sets. Every point is an interior point. Every point has some sort of wiggle room. Okay, and there's a characterization for the open set. So there's a characterization of open sets in R. As it turns out that this is a useful result theorem. Any open set in R is a countable union of open intervals. So the intuition is as follows. So on the real line, the open sets can only look like this. Okay, so we're going to take these as facts and use them freely. So any open set on R must look like this. Okay. And Borel sigma algebra, the notion of Borel sigma algebra is as follows. It's the smallest sigma algebra that contains all these open sets, because the collection of all open subsets themselves do not form a sigma algebra. Okay, check this using the definition of, you can easily check this using the definition of sigma algebra. And now the theorem is saying, the problem is saying, you can describe Borel sigma algebra differently. And if, let's say, S is the smallest sigma algebra containing the subset of this form, R to N, right, open at R, open at the left and close at the right end point, it turns out this is the same collection as Borel sigma algebra. You're not getting anything new here. Even though the description looks different, they're the same thing. So that's, hi sir, hi from Canada. Thanks for joining the stream. So this is what we're trying to solve here. Okay, first of all, let's think about what are these sets. The sets in the the sets, okay, the set says S, okay, S is the smallest sigma algebra, it's the smallest collection of subsets that is a sigma algebra, and it contains set of this form. Okay, so but we can just note that these are sets in what we call, these are Borel sets. These are Borel sets. So first of all, note that for any R in Q and N in Z, R to N is Borel, is a Borel subset of R. Okay, and to see this, we just need to write this as a countable union of open intervals. Okay, so indeed, you can write this as such. So you can write it as such. So for fixed R and Q, for fixed R in Q and in big Z, okay, you can write R to N as a union of intervals of the form R of N minus 1 over K, open interval, and actually, you know what, that's not a good idea. Okay, this actually will never give you N, because if you take the union, okay, so this is what I was thinking. So here, let's take a look at the picture. R and N. R and N. So I want to approximate this set using open intervals. So think about, let's say I just want to push the boundary, the right endpoint, a little bit to the right of N, and then gradually squeeze towards N. Okay. Gets closer and closer to N. So I need to do a plus sign here. Do the plus sign. Instead of union, I do intersection. So K from 1 to infinity. Right. So this is the intuition. Of course, this can be rigorously proved. You just use a double containment argument, which I will not do here. Okay. This is an exercise in the first introduction to proofs. Showing this equality is a basic exercise in the first introduction to proof. So you start from a element in the left set, you prove it's also in the right, and do the other way around. So I would just take this as a fact, okay? And here's the visualization for that. And well, what does it say? It is a countable intersection of open sets. And because we know sigma algebra is closed under countable intersection, so this is in the Borel sigma algebra. So this is the Borel set. Okay, so it is therefore it is in the Borel set of R. In the Borel set of R. So what we have is the following. S is the smallest sigma algebra containing this set, containing these sets, and they are in the Borel sigma algebra. Okay, so let's call this class C. Okay, S contains C. S contains C. C is a class of subset. S contains them, and S is a sigma algebra. S is in fact the smallest sigma algebra that contains them. And what we just see is that C is also contained in the Borel sigma algebra. So Borel sigma algebra has to be at least greater or equal to S, BR. At least greater or equal to BR. So this is what we diagrammatically can represent what we just shown here. So what it matters is since, let's say since S is the smallest sigma algebra, smallest sigma algebra containing, as I said, let's call this class scripted C. Scripted C, Rn, where R is in Q and N is in big Z. This is the smallest sigma algebra. And BR, the Barreau sigma algebra, actually I should use scripted S, okay? I'll try to keep notations consistent. Scripted S. We use scripted letters for the collection of sets, just like scripted C here. Scripted B as well. So scripted B, that's the Barreau sigma algebra. And BR, the Barreau, the collection of Barreau sets, subsets of R, is also a sigma algebra. This means BR must be at least as C. It follows that scripted S is contained in BR. Okay, so why don't we give this paragraph a little name? So the name is S is a subset of Barreau sigma algebra over R. So that's the argument. And of course, to prove the two are equal, we need to show the reverse containment. So we need to show that S contains Barreau sigma algebra of R. So we need to do that as well. So how do we do that? Well, you just need to show every Barreau set. Every Barreau set is what? Is an element of S. Or actually, or can be formed using the elements in S. Actually, this is what I mean. Okay, so to show this, what we want. To show this, what we want. So, well, as I said, the Barreau sets can be seen as a countable union of open intervals. No, that's BS. Sorry, my bad. An open set is a countable union of open intervals. Right? So if we can show that open intervals, our open intervals are in scripted C, then we're done. Okay, let me just write that again. So it suffices to show that open intervals are in C. That's it. Let's think about why. Why this gives us our result. So imagine you already have this result. Open intervals are in C. So if open intervals are in C, then an open set is in S. Because remember, S is a sigma algebra, and S contains everything in C. Okay. Oh, actually, no. Open intervals are not in C. In S. My bad. Open intervals are not in C, because C contains non-open intervals. My point is, My point is, open intervals are in S because open sets are countable unions of open intervals, plural. Here, this theorem right here. And S is a sigma algebra, so the countable union is closed in S. So S contains all the open sets. So S contains all the open sets in R. You got that? Okay. And Borel sigma algebra is the smallest sigma algebra, contains open set. And we just show that S contains all the open sets. So you have the containment right here. Yeah, I can already see viewership is dropping. I know this is typical material. Yeah. So there was, that's okay. That's okay. You can always come back. I mean, this is very demanding stuff. I'm not gonna lie. Okay. Um, it suffices to show open intervals are in S. This is because all open sets are countable union of open interval. Okay, just to be more precise, let's emphasize open sets in R. Okay, open sets in R are countable unions of open intervals, and S is a sigma algebra, which means it is closed under countable union. And S is a sigma algebra, which by definition is closed under countable union. So, yeah. Um, so this no okay. So this will prove that open sets are in S. Hence, this this proves open sets are in S. Okay, S is a sigma algebra. S is a sigma algebra. S S is a sigma algebra, and um, BR is the smallest sigma algebra containing open sets. Hence, S contains BR. Here we use the minimality of BR, and over there we use the minimality of S. Okay, so now it's just a matter of showing open intervals are in S. So can we do that? Can we show that the open intervals are in S? Well, open intervals has this general form AB, right? Has a general form AB, so you can think of it as the intersection. Take this as the intersection of minus infinity minus infinity to A intersect with no, not in minus infinity to B intersect with A to infinity. Okay, so that's our idea. Let's draw a picture for that. Okay. This suffices to show, okay, so now let's prove. Prove that open intervals are in S. Okay. Let's consider the fact A to B open interval is the intersection of minus infinity to B intersect with A to infinity. Okay, draw a picture. A to B can be seen as the intersection of A to infinity and minus infinity to B. Okay. This line diagram is well known in high school. Okay. So consider this fact. And what we know about S is a sigma algebra, so S is closed under finite intersection. Well, it's closed under countable intersection. It has to be closed under finite intersection as well. So we want to show that both of these are in S. So both of these are in S. So here, there's something interesting going on, because the right endpoint of C are all integers. All integers. So to cook up A to infinity is not hard. Remember, A is real. Okay, A is real. So here, A and B are all real. All A, B are real. But let's think about our restriction here. The right endpoint of intervals in C are all integers. So how can we approach that problem? Well, first of all, we can do something like that to get the interval A to infinity. So how do we get A to infinity? Take a look at the picture here. This is A to infinity. Our building blocks are sets of this form. You know what? Let me just put it down here so I don't have to scroll that often. So this is C. Okay, so the right endpoints are all integers. The left endpoints can be rational. Rational is nice because rational can be used to approximate any real. That's the density of Q in R. So I'm saying is, let's think about a way to approximate the interval A to infinity. And this shouldn't be too hard. So for any A in real, there exists a sequence. The sequence, let's call it R of n in Q. So these are all rational numbers. Sequence Rn in Q such that Rn decreases and Rn has limit A. So you can always do this. This is the visual. So this is R1, R2, blah, blah, blah. It gets closer to A. You can always do that. Yeah. Okay, so there exists a sequence Rn such that Rn decreases and approaches A. Okay, and we can just write A to infinity. Then A to infinity is the union of Rn and n, closed interval on the right. And n goes from 1 to infinity. As n tends to infinity, Rn, first of all, these intervals are all nested. First of all, these intervals are all nested. So actually, you know what? Just to avoid situation where this is an empty set, I'm going to write Rn plus n. So this is always non-empty. So Rn plus n. to make sure this is always non-empty. So the first interval is R1 and R1 plus 1. And the second interval is R2 and R2 plus 2. Hold on. R2 plus 2. Can I make sure this is nested? Does it matter? I'm saying is it shouldn't matter. It shouldn't matter. So the idea is for all of these taking union, eventually the right end point blows up. So you get a to infinity. Okay, and of course this is good enough for our goal. Actually, you know what? This is not good because that's not an integer. That's Rn plus n is not necessarily integer. So screw that. Just plus n. Just plus n. That's enough. I mean, even though empty set taking union is not an issue. Empty set taking union is still well defined. You don't need to keep all of them to be non-empty. Okay. A question. We need the right side to be integer. Exactly. 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 So I just fixed that. So this might give us some empty sets, but eventually this will be non-empty because n will be very large and Rn is going down. All right, so this shouldn't have any problem. Yeah, don't be sorry. Like I realized the problem and you also corrected me, which is awesome. Which is awesome. This is what this series is about. Like I'm not lecturing on this stuff, okay? You can think of like I'm I'm showcasing the thought process, which may contain error actually, but I will do the best I can. So what this says is basically a to infinity is an approximation of what? A to infinity is an approximation of sets in C. Right? So a to infinity is a countable union of sets in C. I.e., let's say a to infinity is a countable union of sets in C. Actually, let's put that ahead. So, claim. Let's call that a claim. We claim that a to infinity is a countable union of sets in C for all a in R. Let me just reorganize things a little bit. Yeah, proofreading sometimes takes a little bit of a rewriting as well, just like writing an essay, so that the flow is the best for a reading experience. Because most likely, the future reader of your own stuff is you. And you don't want to confuse yourself, don't you? Do you? Right? So we claim that a to infinity is a countable union of sets in C for all a in real. And let's write indeed. So this way, when you read this later, you immediately know where you're going. Indeed, for any a in R, there exists a sequence Rn such that it decreases to a, and therefore you have this relation. Okay, so every single one of them, so these are all the sets in C, countable union in C. So, and because of S is a sigma algebra, it is closed under countable union. A to infinity is in S. So therefore, we conclude a to infinity is in S for every a in R. So that's cool. And second, we need to work on minus infinity to b. So minus infinity to b needs a little bit of a thought because b is real, right? And our endpoint on the right is, the right endpoint b is real. However, our right endpoint in C are all integers. So that's not good. You can't approximate any rational number. Sorry, you can't approximate any real number using integers alone. That doesn't work. So we think of another property of the sigma algebra. So let's think about the complement. If you can show the complement of this thing is in S, then you're also done because sigma algebra is also closed under complement. So to see minus infinity to b open set, okay, to minus infinity to b is in S for all b, considering the complement. Consider the complement, okay? So positive, sorry, not positive, but b to infinity is what? B to infinity can also be written as some sort of countable intersection, countable union. Right, let's draw the picture. So here, our original goal is minus infinity to b, like this. But now we're considering its complement. So that would be that would be b to infinity. B to infinity. So how do we get a b to infinity using sets in C? Remember, the right endpoint is an integer, and the left endpoint is rational. The rational is where we get the approximation going on. So how do you get the inclusion of b? You need to push the boundary a little bit to the left and then take intersection. So this is how it's done. Okay, so, and actually we just showed that a to infinity is in b and a to infinity is in S. This is perfect. So we can write b to infinity as the intersection of say R. Let's not use R. Let's say Pn to infinity, where n goes from 1 to infinity, where Pn is a sequence of rational such that secant is a sequence of rational such that, I mean, you don't even need rational. You don't even need rational, do you? You don't even need rational. That's overkill. You just need, say, b minus 1 over n. That's enough. B over 1 minus n to infinity. You see, we just showed that the set of the form a to infinity is in S. So b minus n to infinity, these are all in S. And they are now taking countable intersection. So the result is still in S. And because the complement is in S, minus infinity to b itself is in S. Okay, so that's the idea here. So as you can see in this sort of proof, okay, to prove two sigma algebra are the same, or at least something, the real sigma algebra can be described equivalently in terms of another set. One direction is typically a lot easier than the other. In the reverse direction, the crucial result that we use is that Q is dense in R. Because this sequence Rn in Q that approaches A, you can always do this for any real number. This is a fact called the density of Q. which shows up a lot in these kind of proofs. Density of Q and the fact that Q is countable are super useful facts in measure theory. Q is dense in R. And Q is countable. It's also super useful. So overall, we show that A to infinity is always all in S, minus infinity to B is in S. So A intersect B is in S. So overall, therefore, the conclusion is that A to B is in S for all AB in real. What is the measure of a man, though? Is this trolling? I don't know. Like, we haven't defined measures yet. Okay. So, yeah, this is A to B, open interval A to B, and follows what we discussed earlier. So we're done. Okay, so now we can say Barreal sigma algebra is contained in scripted S. So overall, they're the same. Equals the Barreal sigma algebra. And that's the end of the proof. Okay, so the schematic illustration of the second direction is that what's that? Open intervals are in S. Yeah, open interval. So open interval, just write it this way, is a class of subsets of R. It belongs to S. And the Barreal sigma algebra is the smallest sigma algebra. So S is at least as large as the Barreal set. Oops, back to the right amount. The measure of a mouse. Oh, hi Leo. Thank you so much for joining the stream. Okay, sorry. The measure of a mouse. I'm not even sure if mouse is measurable, but anyway, here we have this classic proof, and I strongly recommend that you guys check out the rest of the two exercises, 5 and 6. Okay. Once again, one direction should be easy. First of all of these sets are Barreal sets. These are all Barreal sets. So what does that mean? It means the S is at least as large as the Barreal set. And the reverse direction usually involves some kind of approximation argument. Okay? So yeah, very nice exercise. Now let's continue. I wanted to take a look at this actually, even though this one is not mentioned in the, hold on a second. It is not mentioned in the, yeah, this one actually, 13. I want to do 13. There's so many valuable exercises, man. So yeah, I can actually, you know what? I might as well just spend the whole stream doing exercises because we wanted to make sure we absolutely understand what the hell is a measurable function. Because we don't want to build on sand, do we? Okay, so proof. Suppose X and S is a measurable space. E1 all the way to En are disjoint subsets of X. So let's draw a picture, shall we? So you got this measurable space, big X, and you have a bunch of disjoint subsets. So this is E1, E2, and whatnot. Okay, I think the disjointness will play a role there, probably. En. Okay, so these are disjoint subsets, and you have C1 all these are distinct are also distinct non-zero real numbers. Prove that this is a measurable function. The linear combination is S measurable function if and only if E1 all the way to En are in S. Okay, so let's recall the definition once again. What's the definition of a S measurable function? This is S measurable, C1. Recall the definitions and see if there's, and also, okay, not just definition, but also, is there any shortcuts, usually in the form of theorems, that leads us to this result? Actually, you know what, this is not we're not even there yet. Okay, just a general function. Recall definitions and theorems. Okay, definition. Okay, f from x to r is S measurable if is S measurable if for every set B in the Barreau sigma algebra, the inverse image or the pre-image of B is in scripted S. That is the sigma algebra over big X. That's literally the definition. And there is a theorem which is very nice. We did that last time. Here. It gives us a shortcut because the collection of Barreau sets is still very large. If you wanted to verify, oh, every Barreau set has that property, okay, F inverse B is in there, that would be a very difficult thing to do. Okay, unless for very simple examples. Here, where's the definition? Yeah, right here. Okay, in the definition, it uses every Barreau set. Of course, Barreau sets can still be very complicated, so verifying this can be tricky. Fortunately, we have the following shortcut. Okay, as it turns out that you just need to verify that the inverse image of intervals a to infinity, open set a to infinity, is in S. That's enough. That's enough. So that's a very useful shortcut. So the next result shows that to verify that the function is as measurable, we can check the inverse image of a much smaller collection of subsets. Leo says, but are measurable sets preserved? Yes, you're absolutely correct. Leo, here. That's actually a theorem. Every continuous function is Barreau measurable. So that's exactly what you just said in chat. The inverse image, the inverse image of measurable sets in R are still measurable. Are still measurable under continuous functions. If f is continuous, yes. It's a big theorem. Continuous functions are measurable. Exactly what you just said. If you take a Barreau set in R and consider its inverse image under a continuous function, it will still be Barreau measurable. Okay. Actually, here there's a caveat here. So we're talking about continuous function from R to R, basically. It says every continuous real value function defined in a Barreau subset of R is still Barreau measurable function. Okay, so that question is answered. It's in the theorem. Okay, so now we're going to use this fact. 2.39 is used a lot in the proofs for many of these results. Actually, you can see here in the theorem we just mentioned, it uses 2.39. So we're going to use that for our purpose as well. So let's do that. So this is theorem 2.39, super useful result. It says if f inverse of b, not every inverse, if f inverse of a to infinity, all right, is in S for all a in real, then f is S measurable. All right. So we just need to check measurability of a much smaller class of subsets. So that's cool. All right. So let's get started. So to prove this, how should we proceed? Well, you have a bunch of distinct real numbers, so let's draw them on a axis, shall we? I guess we can, without loss of generality, assume C1 is less than C2 and blah, blah, blah. You can do that. Because if these numbers aren't in order, you can always order them and relabel the indices. So let's say this is C1, C2, all the way to Cn. But these are so now the numbers are in increasing manner. All right. So what does a to infinity look like? Well, a to infinity is a semi-infinite interval. Right, so this is a to infinity. As you can see, when you change a, you run a throughout real. So it's imagine you start from the very left endpoint. What would be the pre-image of that? Right? Because we're interested in the pre-image. If it's all the way to the left, then the pre-image of a to infinity are what? Well, the pre-image of a to infinity is really just the pre-image of the set C1, C2 all the way to Cn. Because the function can only take these values. Can only take the value C1, C2 all the way to Cn. These are distinct. If if let's say if you are in the set E1, it's just C1. These sets are all disjoints and the values are distinct. If your point is in E1, it just equals C1. If your point equals, if your point is in E2, it just equals C2, all the way to if your point is in E1, the function is just Cn, is in En, sorry, and your point is, your function is just equals to Cn. If it's none of these points, then the function is 0. Right? Then the function is 0. So actually, you know what? We need a 0 here. We need a 0 in this sequence here. So can we say without loss of generality, assuming they're all positive? They're non-zero. These are non-zero. So 0 is somewhere among them. 0 is somewhere among them, but that's okay. We can handle that. Just let's just, okay, I'm not going to say without loss of generality, but let's just say arrange the set 0 union C1 all the way to Cn, okay? C1 all the way to Cn. In ascending manner, in ascending order. Okay, and relabel the numbers as d1 all the way to dn plus 1. As d1 less than d2 all the way to dn plus 1. Okay, just for ease of writing. Okay, there you go. So this is a diagram here. Pretty much the same, d1, d2 all the way to dn plus 1. Okay, as I was saying, so imagine if you run the left endpoint a from minus infinity to all the way to infinity, what would happen to the inverse image? So initially you would have what? Initially, actually, you know what? It's still hard to describe because we don't know what, if any of them, what's the relationship between them and zero, huh? Actually, let's actually, you know what? Let's set our goal to be, because this is an if and only if statement. We need to prove both directions most of the time. So let's just say, actually, you know what? I wanted to look at the cases of all possible cases of the f inverse of a, of f inverse of a to infinity. I want to write this as f inverse of sorry, f inverse of a to infinity equals, I think there should be a bunch of cases and a to be in whatever range. Okay, so we want to do that, and d, so actually, can we say it is just a, it's one thing to discover the idea of a proof and it's another thing to write it down. Okay, so um, I'm um, I'm just gonna right now. I'm just gonna to not worry about the formality and just say, okay, say zero is the smallest. Say zero is the smallest. My goodness. Say zero is the smallest, and you have C1 in all the way to Cn in ascending order. Okay, so what comes now? A to infinity will have the inverse image of just the whole of big X. Just the whole of big X, right? Because all of these numbers, C1 all the way to Cn, assumed to be positive, and a is less than 0, so the inverse image is the whole set, because for any point in big X, its function value is always going to be at least 0. So if a is negative, the inverse image would be the whole of X. Okay, so if a is negative, then the inverse image is going to be whole of X. Okay, so if, let's say, if a is positive, if a is greater or equal to 0, what happens? Actually, it should be less than or equal to 0. No. Let me think about this clearly. Can I put equal sign here? Actually, I cannot, because if a is equal 0, if a equals 0, say f inverse of 0 to infinity, that cannot take function value 0 there, all right? So that means it cannot be, it has to be in one of the E1 all the way to En. It cannot be in the in the in the in the complement region. Right, so here this should be strictly less than 0. Strictly less than 0. Okay, so if, and now next up, so let's say a is greater or equal to 0, less than or equal to C1. Less than or equal to C1. So, yeah. So if it's less than or equal to C1, then what happened? Less than C1, perhaps. That's a good idea. So less than is greater or equal to 0 and less than C1. Okay. If that's the case, so A is greater or equal to 0. So it cannot, the left end point cannot be 0. It can be 0. It can be 0 to infinity, right? So this is possible. This is possible, but it's still less than C1. It's still less than C1. So A is somewhere here, looking at the picture. So, yeah, this is A. A is somewhere here. What's the inverse image of that? Well, it can't be 0, but it can't be C1 all the way to Cn. Therefore, the inverse image is the union of E1, E2 all the way to En. E1 union E2 all the way to En. Okay, so you can see where the pattern is going. And if you move A further to the right, say now you're past C1. A is greater or equal to C1 now. Then suddenly E1 can be taken. The inverse image will not include E1. Right? So as you can see, as A increases, the size of the no, not the size, but just the pre-image itself shrinks. It starts from the largest possible set, just big X, and it goes down. So when A is greater or equal to C1 less than C2, it will be E2 union all the way to En. And finally what you have, well, finally let's say A is greater than Cn, greater or equal to Cn, then what? It's just the empty set. Okay, so this is just a relation of pre-images. Nothing else has happened. Okay, we never talk about measurability at all. Here it says, and this function is a S measurable function if and only if all of these sets are in S. So clearly you can see, well, if all of these sets are in S, then on the right hand side, in every case, the pre-image is in S. So it verifies the condition in 2.39. So you're done. Right, so you're done. So, and now, I mean, you can, if you go the other way around, say, if the function is measurable, okay, so if the function is measurable, that means the f inverse of A to infinity should be measurable. Should be or all in S, right? They should be all in S. Right? They should be all in S, and indeed say you can always extract. You can always extract, say, E1. You can extract always, say, E1. You can just take the difference between E1 union E2 all the way to En and E2 all the way to En. Take the set difference, you get E1. And this way E1 is in S. This way E1 is in S. And in the same method, you can extract E2. So now you have proved that E1 all the way to En are in S. So that's the idea of the proof. Okay, so this is what I was saying. It's one thing to discover the idea of a proof and another way to write it down nicely. Both are equally important. Okay, it's not enough for you to appreciate, as an individual, to appreciate and realize the result is true. You have to communicate it properly. Otherwise, the result just dies. So how do we write this nicely? Right. So I think perhaps a nice way to attempt this is to look at induction, because this is a statement regarding integers, right, or natural numbers. So perhaps it's a good way as a writing strategy. Let's use induction, even though the main intuition is already clear. So all of this should be considered as scratch work. So this is scratch work. This is scratch work. So now let's write the formal proof. Using induction. So we prove it, okay, using an induction on N. Okay, so there you go, the base case. The base case where n equals 1. N equals 1, that's the simplest possible situation because we have a theorem in the textbook. have a theorem in the textbook. So you want to show that just C1 chi E1. C1 chi E1 is measurable. You need to show C1 chi E1 is measurable if and only if E1 is measurable, or E1 is in S. And that's a readily usable result here, right here. That's the example, 2.38. Right? So chi E, that's an indicator function or characteristic function. This is S measurable if and only if E is in S. So let's write that by example 2.38, chi E1 is measurable Oh, actually, here we also have C1 non-zero. Okay, so yeah, so chi1 is measurable if and only if E1 is in S. Okay, and this is equivalent to, because you can always multiply a constant and still get a measurable function. Say chi E1 is measurable also for any C1 non-zero. Chi E1 is measurable if and only if C1 chi E1 is measurable. Okay, so this is cool. Okay, so you have that. So therefore, you're done. This finished the case of the base case. All right. Yeah. By the way, just wanted to emphasize where we got this result. This is because of composition. This is because of composition. To justify this step, we can say, indeed, can say indeed. We have a result earlier that has to do with composition. Right here. Composition of measurable function. It says if f is measurable and g is measurable, then the composition f and g is measurable. Right? So this is because you can write f of x equals c1x is continuous and thus measurable. Continuous and thus measurable, which we used as this result here. Leo asked that question right here. Hang on, 2.41 by 2.41. Okay, and C1 chi E1, this equals the composition of F circle chi E1. The composition is thus measurable. And the theorem for composition is 2.44. Okay, so that's done. And that's the base case, right? So now we need to do the inductive case. To do the inductive case, so how do we proceed? Inductive step, all right? Inductive step. So let's first write down the induction hypothesis. We assume there exists for some k, Okay, assume for some k in a set of natural numbers, okay, you have let me just write down the whole sentence. So E1, if E1, okay, if E1 all the way to EK disjoint, is that disjoint, and C1 all the way to Cn distinct, non-zero, distinct, non-zero, we have the following, not Cn but Ck. Suppose this is true. They're distinct, non-zero. You have a C1 chi E1 plus all the way to Ck chi Ek as measurable if and only if E1 all the way to Ek are in S. So that's it. So that's the induction hypothesis, call it IH. And which to prove you can go from K to K plus 1 essentially. Okay, so how do we get there? So how do we get there? Well, let's think about, say, now suppose, okay, so we need to show this is true for K plus 1. So suppose E1 all the way to EK plus EK and EK plus 1 are disjoint. And C1 all the way to CK plus 1 are disjoint. CK plus 1 are disjoint. Not disjoint, but distinct. Non-zero. Okay. We want to show the equivalence. Need to show you got C1 chi E1 plus all the way to CK plus 1. No, sorry, CK, yeah, just say CK chi EK plus CK plus 1 chi EK plus 1 as measurable if and only if E1 all the way to EK plus 1, these are in S. So yeah, this is what we want to show. I guess you can use the inductive hypothesis. Actually, you know what? Never mind. Can we at least get one direction done? Can we at least get one direction done? So assume this is S measurable. Okay, so anyway, let's say, I don't know which direction would be most convenient. Let's just assume the backward direction. So now let's assume all of these are measurable. Assume E1 all the way to ek are measurable. E1 all the way to ek, sorry, ek plus 1 are measurable. Okay, and the grand hypothesis is that they are all distinct. They're all disjoint. Okay. So I guess from the induction hypothesis, because of E1 all the way to EK are disjoint, you can say that the sum of the first K terms is measurable. By induction hypothesis, we get that C1 chi E1 plus all the way to CK chi EK, this is S measurable. Okay, this is S measurable. So we have that. And now we just want to show that adding this extra term here is still S measurable. So how do we do that? Actually, guys, am I stupid? I'm probably stupid because I just figured it really say it's really a matter of applying this property. Guys, I think I'm stupid. I might be mentally challenged actually. Sorry about that. So we have this big result. It tells us the sum of two measurable functions is measurable, and you just use induction on that. Use induction on that to get finite linear combination gives you a measurable function. All right, so that's embarrassing. My goodness, you don't need this induction business. I mean, you do need the induction business. It's just that it actually has nothing to do with the characteristic function at all. Yeah, it actually has nothing to do with. Oh, never mind. Actually, maybe it has something to do. Okay, I was just having an existential crisis over what I just did. If you have E1 all the way to En are all in S, then each individual chi function, the characteristic function is measurable, and linear combination is still measurable because of the fact that the set of measurable functions is a vector space. You can say that, right? You can say so one direction is immediate, so you just need to prove the other direction. The other direction goes as follows. So assume this is what we call it, measurable. Yeah, assume this is S measurable. We want to show that all these sets used to define the indicator functions are all in S. So I guess you can modify the proof as follows. So I'm going to change the proof a little bit, okay? So we still need the induction, I believe. We still need the induction. Here, you just want to say something like the if direction is trivial. The if direction is indeed trivial. Indeed. Indeed. So chi ek is measurable. Chi ek is as measurable. So the if direction assumes you have E1 or to En measurable. So indeed measurable if ek is in S. And this is true for all k in 1, 2, all the way to n. Linear combination by the linear combination of a measurable, a linear combination of measurable function is still measurable. As measurable functions is as measurable. So that's the obvious direction. So that saves us some work there. And for the only if direction, we prove it using induction on it. So that's perhaps more economic. For the only if direction, we use an induction on it. We use an induction on. So that's the idea. Okay. And we have, okay, let's rewrite the base case. So, well, the base case is now as follows. So for n equals 1, assume C1 chi-E1 is measurable. Assume this is measurable. And C is non-zero. Need to show E1 is in S. Just going to change that. Okay. Need to show E1 is in S. And of course, this is very easy. So you can write it as follows. You can write it as follows. So chi-E1 is 1 over C1 times C1 chi-E1 is measurable. Here, S measurable and measurable are the same thing, actually. Let me just actually put the S measurable up here. So this is S measurable. So therefore, by the example 2. Hang on a second. Yeah, by this example 2.38. By 2.38, E1 is in S. So we're done. So base case is done. And now we need to show the inductive case. So assume for some k in big N, if E1 all the way to En are disjoint, C1 all the way to Ck are distinct, non-zero, we want to show the only if direction. So we just need to show the forward direction. So this is our goal. Suppose E1 all the way to Ek plus 1 disjoint, C1 all the way to Ck plus 1 distinct, non-zero, need to show. You have this linear combination of k plus 1 characteristic functions being as measurable. We want to prove that E1 all the way to Ek plus 1 is in S. So this is what we want. So yeah, this is what we want. And can we perhaps use a little bit of a help from the induction hypothesis? Because you must use that. You must use the induction hypothesis. Well, you don't need the backward direction anymore. This is unnecessary. So, okay. Um, assuming this is measurable, you want to show that all the way, E1 all the way to EK plus 1 is an S. Okay. By adding this extra term, the function changes by what? The value of, by adding an extra term to the right, the image of the function or the range of the function add exactly one number to it. Add exactly one number to it, and is also yeah. So that's what we're handling. So by the induction hypothesis, okay, let's say start with assuming the basic proof writing. Back to basic, assuming the if part, and then prove the then part. Assume C1. Okay, let me just copy it. Assume the if part. Then what happens? Well, I guess you can say, assume this is measurable, and now that you have the last term is also measurable, since the last term is also measurable, you can get that the the sum of the first two k terms is measurable, right? So we wanted to cook up an environment where you can use induction hypothesis. Since ck plus 1 chi ek plus 1, this is measurable. Do we have that though? We don't. We don't. We need, because if you assume this, you already know. Because if you assume this, you already know that ek plus 1 is an S, which you cannot assume. I was trying to say, oh, the last term is measurable. So the difference between this and the last term, which is the sum of the first two k terms, is as measurable. Then you can use the induction hypothesis. So suddenly all of E1 all over EK are in S. But you cannot do that because we don't know at this point whether EK plus 1 is measurable or not. You can't do that. This is such a pain in the ass to write. Okay, sorry. How do we cook up the argument here? Assume this is S measurable. Maybe use strong induction? Maybe use strong induction? I guess you can say, assume for some k, if assume for some k, if for all little l less than or equal to k, E1 all the way to EL distinct, C1 all the way to CL distinct, non-zero, the sum of L terms, where L, as I said, L is less than or equal to K. The sum of L terms as measurable implies that E1 over the EL is an S. Can we do that? I'm actually struggling big time right now. So, do you, can I say, this intuition is excellent, but how do I convert that to an actual formal proof though? If in the inductive hypothesis, I assumed the you you have the result holds for n equals k. And how do you cook up a function with k term that's measurable? That's the issue here. Can you say things like that? It's right in our face, right? It's right in our face, but writing it is still a challenge. You know what, guys? I'm going to AI because I don't want to get stuck here forever. So let's see if we can get some help there. All right. So what we're saying is, what we're trying to say is, okay, so can we, so this is here's the problem. Here's the problem. Okay, so let n be and be a natural number. A natural number, a natural number, and actually first let x scripted as be a measurable set. Measure measurable space, yeah. Let n be a natural number, suppose. So let's say, yeah, suppose E1, suppose E1 all the way to En are subsets of X, and which are distinct or disjoint. Disjoint. This is important. Disjoint subsets of X. C1 all the way to Cn are distinct non-zeros. Zero numbers. All right. So show that the linear combination C1 chi E1 plus all the way to Cn chi En is measurable, is S measurable? S measurable if and only if E1 all the way to En are in scripted S. So the problem is I tried induction argument, but it didn't work. Doesn't seem it couldn't make can make it work. All right, so let's see. The key is to exploit the coefficient of distinct and non-zero. Yeah, so in the base case we already used C1 is non-zero. See? Because if your C1 is 0, then this cannot be used. If C1 is 0, then the function is always 0. Right? It's always 0. So the constant function is always measurable. The constant function is always measurable, and you can put a non-measurable set, a set that is not in a set E1 that is not in the sigma algebra. Okay, and still because of C1 is 0 in that case, the function is still measurable. So if C1 is 0, you cannot get E1 in S. And we use that fact here. So 1 over C1 is non, 1 over C1 requires C1 non-zero. So here it says, this is a key. Induction proof is possible, but it's a much cleaner direct argument, actually. Okay. So this is F, and you have F of X is Ci. X is in EI. Yes, we have the image. We have the diagram, the sketch that shows this, right? So the assumption is that Ci is all distinct and non-zero, exactly what makes each value correspond to a unique set. All right, suppose F is measurable. All right, suppose F is measurable, then you have what? And the singletons, yes, the singletons are EI. The singletons are EI, yeah. And conversely, if F of, let's call that Ci, okay, if F of X equals Z, then X cannot belong to any EJ, yeah, because of disjointness. Oh, okay, okay, and now we have what? Oh, actually, it's very short. It's just this part. That's enough for us. That's enough for us. So, okay, actually, this is overly complicated. This is actually not very useful. I mean, what we wrote here was actually a complete. I mean, it's possible, as I said, it's possible, but this is awkward. This is awkward. So let's get rid of all of that. I think I committed to this theorem. I committed to this theorem, which is useful for a lot of situations, but actually unnecessary here. Unnecessary here, because we just need the inverse image of the singleton. We just need the inverse image of the singleton. So this theorem 2.39 is actually overkill here. This is actually overkill. So I think we just need the definition. The singletons are a Borel set, and that's enough. Okay, so it's coming back to this exercise. Let's redo this. Once again, the if direction is trivial. So that part of our work is okay. The if direction is trivial. Indeed, if EK is in S, then chi EK is S measurable. Okay, chi EK is S measurable for all K equals 1 all the way to N. And a linear combination is always measurable. Linear combination of a measurable function is always measurable. And linear combination of measurable functions is always measurable. So this proves the if direction, the only if direction. So now the only if direction. The only if direction is actually a lot easier because you assume this is measurable. I mean, I was stuck with the theorem 2.39 theorem 2.39. Why is this theorem 2.39 is unnecessary? Why is this big high caliber weapon is unnecessary? Because this is for checking measurability. 2.39, this is completely unnecessary. The big theorem is for checking measurability, you see? This is for checking measurability. However, the measurability here is trivial. It's a linear combination of measurable functions. So we're done here. And to prove the only f direction, you're assuming f is measurable. You just need to show these sets are in S. So theorem 2.39 is useless here. Okay, so I committed to a wrong path. 2.39 is rendered completely unnecessary. So the only f direction is remains to be proved. Okay, remains to be proved. So let's do that. Okay, so the f of x for each x in big X, f of x equals ci. When x is in ei, I equals 1, 2, all the way to n. And if x is in the complement, that is x minus the union of ei, I from 1 to n, this is just 0. So this is the value of f of x. So, and now use the fact that ci's are distinct and non-zero. Since ci's are distinct and non-zero, f inverse of the singleton ci is ei. So ci, the value ci can only be attained in the set ei. And since the singleton ci is a Barreal set, and S and F is measurable, the only if direction assumes that S is the function is measurable. So yeah, write f of x to be the sum of the linear combination basically. So f of x is now needs to be defined. It's defined as the sum of ci chi exi, I from 1 to n. So this is a Barreal set and f is S measurable. ei belongs to S. And you're done here. That's it. That's it. We need to show all the are in S, so we're done. Okay, it's really that simple. Okay, so why did I make such a long detour without realizing it? Because I committed to this theorem. I committed to this theorem for checking measurability. Because we've seen a lot of propositions being proved using 2.39. But this is unnecessary because this is for proving f is measurable function. Here, the measurability is trivial. If you have each ei is in S, then each term taking linear combination is measurable. So linear combination of measurable functions is always measurable. You don't need 2.39. And now, if you just need the only if direction, so if you already have the function is S measurable, using the fact that CI's are disjoint, EI's are CI's are distinct, non-zero, and EI's are disjoint, you can easily specialize the inverse image to be EI simply by picking the inverse image of a singleton. So there's that. Okay, so that's embarrassing. Well, this is that's okay. We're not going to sugarcoat anything. So and now I wanted to take a look at the next exercise because remember on the last stream we did the limit of a S measurable function, I was trying to justify the, I was trying to justify this, not justify, but motivate this construction. This construction is, of course, exceedingly clever, right? Because once you've written the F inverse of A to infinity as a countable union and counterinterval intersection, this is automatically a measurable set. So we're done here. So you just show this identity and you're done. But I was having a hard time thinking about, okay, how on earth can anyone think of this construction? Well, I didn't think I came up with a good explanation to motivate this proof, but today we'll try with a different example. Not an example, but an actual question. So this one, this is the 14, because if we can't do that, next time we've seen it, we still can't prove it. Okay. Even though if you can, even though, I mean, verifying the identity isn't too difficult, but it's very hard to come up with this identity, if you know what I mean. Because this identity solves the whole proof. Okay, so let's do this question, because this feels very similar to that particular exercise. So it says, suppose f1, f2, all the way, the sequence of functions from a set x to R. Explain why this is true. Okay, explain why this is true. So the set of x in big X such that the sequence, okay, so here imagine now you're fixing x, and we're saying that the sequence f1 of x, f2 of x, so these are just sequence of real numbers. This is just a sequence of real numbers because now x is fixed, has a limit in R. So what we're saying is, so imagine you have this little diagram going on. So the horizontal axis is big X. It doesn't have to be a subset of R, okay? By the way, just an arbitrary set, big X. And the sequence of function is a bunch of curves, a family of curves. It doesn't have to be continuous and all of that, okay? It doesn't have to be. It's just saying that we are looking at the point, little x in big X, such that, let's say this is f1, f2, f3, blah, blah, blah. Okay, the points f1 of x, f2 of x, f3 of x, okay, f4 of x, and whatnot, has a limit. We're looking at the set of the input where fn of x converges. So this is what we're looking at. And that set can be written as this, as say. So explain why this is the case. All right. So, I mean, this is, I guess, once again, I was saying that this shouldn't be too difficult to verify. You just need to use a double containment argument. You just need to use a double containment argument. And so why don't we start from the right? Because on the right, it feels like you have more stuff to work with. So let x to be in the set on the right. So that's the intersection n from 1 to infinity, the union j from 1 to infinity, the intersection of k from j to infinity, okay, and fj minus fk, taking the inverse of the set minus 1 over n, minus 1 over n. I think this has something to do with the Cauchy sequence, I believe. Because here you never said what limit is that. You never said what limit is that. Is it right? Because if it's a standard trick in linear, or not linear, but real analysis, that if you know something converge, but you don't know the limit. Okay, if you know that converge, if you don't know the limit, you work with a Cauchy sequence. You work with the fact that it's a Cauchy sequence, because there's a theorem in real analysis says a real sequence is convergent if and only if it is Cauchy. Actually, let me write that down. I think it will be useful. So this is background knowledge. This is background knowledge. So in real analysis, you have this result that a sequence is convergent if and only if it is Cauchy. Actually, let me just write down all the necessary definitions here. So let's write let Xn be a sequence in real. Let Xn be a sequence in real. The definition of a convergent sequence says the following. So Xn converges to X if let X in big R. Let X in big R. Okay. Xn converges to X if for every epsilon greater than 0 there exists a big N natural number such that whenever little n is greater or equal to big N, you have Xn minus little x is less than epsilon. So that's the definition of convergent. So if such X exists, we say Xn is convergent. If such X exists, but you don't know exactly the value, you can still call it Xn is convergent. Xn is convergent, okay? That's the definition of convergent sequence. And the second definition has to do with Cauchy sequence. So let Xn be a sequence in R. We say Xn is Cauchy, or is a Cauchy sequence if the following is true. If this is a Cauchy sequence, it's a Cauchy sequence if the following is true. For every epsilon greater than 0, there exists big N in a set of natural numbers such that whenever little n and little m is greater or equal to big N, you have Xn minus Xm absolute value is less than epsilon. So they look very similar. The thing is, a Cauchy sequence does not require mentioning a limit. You see, Cauchy sequence, roughly speaking, is the sequence whose terms are getting closer and closer to each other, whereas a convergent sequence is a sequence in which the terms are getting closer and closer to a known point, an external point. So this X, by external, I mean X doesn't have to be a sequence member. Quite often the limit is not in the sequence itself. Right? So that's the difference between convergent and Cauchy sequence, but it turns out that in R they are the same. So this is a big theorem. Actually, you can consider it an axiom as well. It really depends on how you formulate the theory. But basically, a defining characteristic of R is that convergent sequences and Cauchy sequences are exactly the same. It says Xn is convergent if and only if it is Cauchy. It is convergent if and only if it is Cauchy. So this is called the Cauchy criteria. Criterion, okay, Cauchy criterion for convergence. It's pretty useful. Okay. I would like to stress that this is a characteristic of the set R. So this is also called the completeness of R. As a theorem, it is called the Cauchy criteria. As an axiom, it is often called the completeness of R. Remember, completeness of R can have different formulation. We formulated the completeness of R in terms of the least upper bound property. The least upper bound property is one way to say that R is complete. Intuitively, it means R has no holes. Right? But there's different way of saying that. There's actually several equivalent way of saying that. And the other one is in terms of the Cauchy sequence. If all the convergent sequence, if all the Cauchy sequence converge, then then you have then it also defines R basically. In general, it's true that a convergent sequence are Cauchy. Convergent sequences are Cauchy, even in a set of rational numbers. Okay, even a set of rational numbers. Let's say if you have a, a rational number sequence that also converges to another rational number, then the sequence is also Cauchy. However, if you only consider the set of rational numbers, the Cauchy sequences may not converge, because a Cauchy sequence of rational may converge to irrational, which is not, well, rational. So in general, Cauchy sequence is a weaker condition compared to convergent sequence. But convergent sequences are always Cauchy. It's in R where you have two things that are equivalent, and that's called the completeness of R. So here's a little bit of background here. And here, why do we care about this? Here it says the sequence f1 of x, f1 of x, f2 of x, blah, 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 has a limit in R. This is the same as saying fn of x is Cauchy by the Cauchy criteria. This is Cauchy. And now you can use the definition of Cauchiness to understand what is going on here. All right, this is Cauchy. Fn of x, this is a Cauchy sequence. Right, so this is the background here. And now let's consider what is happening here. Right, so if we want to show the sequence f1 of x all the way to fn of x, this has a limit in R. We just need to show fn of x is Cauchy sequence. This is a Cauchy sequence. So let x in this set on the right hand side, we claim that, okay, fn of x is a Cauchy sequence. Weren't you just streaming yesterday? Yeah, I was. I mean, actually, I had two streams today, just today. So yeah, right now, recently, I've been doing this quite frequently. And to be honest, well, Tuesday measure series is like fixed. It's not something I do extra. Okay, Tuesday measure series is like a staple of the channel. So right now we're at episode 6. You can see from the title. We claim that fn of x is Cauchy. We claim this is Cauchy, okay? And now we just need to show this, okay? Follow the definition. So follow the definition. So, okay, what do we mean saying x is in this big complicated set? Well, just unpack the operators one at a time. So if this is Cauchy, do you work? Yeah, right now, I mean, I'm on vacation, so I have more time with the YouTube stuff. So yeah, here you have, this is Cauchy. Yeah, this is Cauchy. So let's, oh, no, actually don't. We don't have that. We claim this is Cauchy. We need to show that. So by this hypothesis, we know that for every, so by star, okay, let's by star. By star, for every n, in big N natural numbers, x is in this set right here. Okay. So for that, let's just pick an epsilon greater than 0. Let epsilon greater than 0. Let epsilon greater than 0. So we're going to check whether there exists a big N such that m and n greater than big N, xm minus xm less than epsilon. Okay, so what I'm saying is, can we say there exists is in Actually, let's do that later. Okay, let's keep unpacking this notation. I'm sorry. So let's try to keep unpacking this notation. So here, therefore, it means for every n in big N, so X is now in a union. X is now in a union, which means there exists some J in big N. There exists some J in big N such that X is in the last intersection. This is what we're doing. So we're just unpacking the set operation here. So infinite intersection means X is in all of them, okay? And infinite union means X is in one of them. Okay, actually, you know what? Right, like this, okay? So, all right, so what does that say? Well, this says for all n in big N, or all n in big N, there exists J in big N. Once again, here is the infinite intersection. What does that say? It means for all k greater or equal to, for all k, okay, for all k greater or equal to j, X is in the inverse image. Can you please show task A again? I'm doing it. I'm still doing it. I'm not doing part B. I'm still in part A. Actually, I'm showing the set on the right hand side is a subset of the set on the left. Okay, so you see, I'm starting from an arbitrary point X on the set on the right. I'm trying to prove the left. Prove it has a limit. And I'm using the Cauchy criteria. That's why I spent all this time talking about Cauchy sequences. Because this feels awfully similar to a Cauchy criteria to me. Okay, so Andre, here, okay, no worries. So here, I'm saying that X is in Fj minus Fk inverse minus 1 over n to 1 over n. Okay, there we go. Okay, there we go. So, what does this mean? What does this means? I.e., keep all these quantifiers. It's going to keep all these quantifiers above. Okay. Just some basic manipulations of set, logic, and functions. This is why fundamentals are so important. Fj minus Fk, the function Fj minus Fk evaluated at x is in minus 1 over n and 1 over n. Okay? And what's that? And what's that? Okay? So I was saying that you just, all right. I was saying that you can bring this pretty much to the definition of a Cauchy sequence. Okay? So this, if you distribute Fj, so Fj of x minus Fk of x is greater than minus 1 over n and less than 1 over n. So it will be absolute value less than 1 over n. It will be absolute value less than 1 over n. So there you go. You pretty much have it. You pretty much have it. So compare this with the definition of Cauchy sequence. This is a Cauchy sequence. You say, this says Fn of x is a Cauchy sequence. Actually, there's a little bit of a difference, huh? There's a little bit of a difference. Let me take a closer look at this. There exists, this this implies, let me say, this implies, or we say claim this is a Cauchy sequence. We already wrote that sentence. We wrote that sentence. So here, let me just keep everything here. This is fairly mechanical. Everyone should be able to do this. So all these implications should be doable for everyone. So this is a completely inevitable process. No mystery whatsoever. And now we wish to show that this is Cauchy. We claim that this is a Cauchy. Okay. So you want to show for every epsilon greater than 0 there exists big M blah blah blah. So let's do that. So let epsilon greater than 0. So we want everything down here to be less than epsilon. So you have less than 1 over n. So we can cook up a big N. We can cook up a big N such that 1 over big N is less than epsilon. You can always do that. Pick big N in the set of naturals so that okay, 1 over big N is less than epsilon. Is less than epsilon. So okay, and now let's see what happens. We wanted to show that for every little m and little n greater than big N, we hold on a second. So we want f of fn of x let n and m to be greater or equal to big M. So, and let's calculate f, say f of actually to be greater or equal to big M. So by this property here, there it says by this property every little n in big N. I want to convert this to the definition of Cauchy sequence. Hang on a second. So now, okay. So because this is true for all little n, so we can say there exists a j. I just woke up to see the measure to click, of course. Yeah. Thank you very much for joining the stream. So exists a j. There exists a j. So log-key. So we're in this doing this exercise. It looks horrendous, but this is actually a very common trick, okay, in all kinds of proofs in measure theory. So you want to write a set in terms of countable union and countable intersection. This is what we want to do. Okay, this is what we want to do. So here we are starting from the set on the right, assuming x is in this countable intersection combination of iterated operation of countable intersection, countable union, and all of that. And you can easily unpack x in this set as a statement of mixed quantifier. You can easily do that. So that's not a mystery here. And what we want to show is x is in the set on the left. That is to show that x has a limit. X has a limit in R. To show that x has a limit in R, and here we did a brief review of the Cauchy criteria in R. The Cauchy criteria says a sequence is convergent if and only if it's Cauchy. So I just wanted to show that fn of x is Cauchy. So that's why we claim that fn of x is Cauchy. But so to do so, we of course have to make use of the final statement. Let's call it star. I want to make use of the final statement. So you want to make things, you want to show that, okay, everything's no. So you want to show, okay, for every epsilon greater than 0, there is a big N such that n and m greater or equal to 0, xm minus xm is less than epsilon. This is what we want to do. Thank you very much for confirming your understanding. Okay, so let epsilon greater than 0, this corresponds to this quantifier. And so we want something like less than epsilon. So why don't we just give ourselves a big N such that 1 over n is less than epsilon. This is always doable. And now we're going to use this property by star. By star, there, I'm going to say, because star works for all little n, right? So I'm just applying star to big N. So there exists a j in big N such that there exists a j in big N such that for all k greater or equal to big J, okay, fj of x minus fk of x, absolute value is less than 1 over big N. So I'm applying the statement star to little n equals big N, specialize that, okay? And let's see what we can go from there. Let's see what we can go from there. So well, you see, in the definitional code sequence, it's not quite enough for, unfortunate class name. I guess you can. You see, I used double strike. Cat walked onto my PC. My goodness. So this is big N. Okay, so perhaps this is clear. Okay, double strike. Double strike letter stands for the natural number. Sorry about that. This is so common. Right? This is so common in analysis that no, we just do this. All right. So I mean, this is very close, but still not quite there yet. We need both index to be greater or equal to big N. So do we have that here? Do we have both index, let's say, k and j? Yeah, that makes it clear. I mean, I know, like, I want, it's not, I mean, the thing is, it's not enough for, say, for all epsilon greater than 0, there exists a big N, such that for all x, for all n, for all little n greater or equal to big N, you have little x of little n minus x of big N, absolute value less than epsilon. That's not enough. You need all the pairwise difference for terms whose indices are greater or equal to big N to satisfy this inequality. We need that. But here it feels like what? Here it feels like we only have, for k greater or equal to, see, for k greater or equal to j, for k greater or equal to j, that's not good. That's not good. So for k greater or equal to j, you have that. But what we really wanted, okay, so it should be for all KL, okay, for all KL greater or equal to j, you have fjx minus flx less than half n. Do we have that? Let's try. Okay, let's try to prove it. Okay, so but basically this is what we get from star. So this is still true, but this is not the same as what we wanted. But I think we're okay. I think we're okay. Andrei says maybe we should introduce PQ. Yes, yes. I think I think Andre is very close to what I'm about to write. Okay, so now we have that. And suppose k and l are both greater or equal to j. Suppose that. Let's consider the difference between fk of x minus fl of x. Taking absolute value, then you can cook up a triangle inequality. Want to cook up a triangle inequality, and this way you get so fk of x minus fj of x, absolute value, plus fl of x minus fj of x. All right, so this is less than half n plus half n, not half n, 1 over n less plus 1 over n. This is 2 over n. And that's actually what we needed. And that's actually what we needed. And to compensate for the 2 over n, we are going to modify our definition for big N. So we modify our definition and say, let epsilon greater than 0 pick big N in natural numbers such that 2 over n is less than epsilon. Such that 2 over n epsilon. So, and this is now less than epsilon. So now we have all the ingredients we need in the definition of Cauchy sequence. You see, the arbitrariness of epsilon, the existence of big N, actually the existence of big J, the existence of big J, the existence of big J, and you have for every, as long as k and j are greater or equal to L, fk minus fl is less than epsilon. So this is Cauchy. So we're done here. Okay, so let me erase this part. So sometimes writing down our goal is helpful. You just need this extra triangle inequality argument in there. Because this in itself is not Cauchy, the definition of Cauchy. Okay, so I think we're good here. Yeah, this is Cauchy. This is Cauchy. So we managed to show this is Cauchy, and thus by the Cauchy criteria, by the Cauchy criterion, fn of x is convergent, or should we say has a limit in R. Same thing. Okay, so that's done. And for the reverse direction, I think we're doing something very similar here. For the reverse direction, we just need to repackage the definition of Cauchy sequence in the form of a set. So we're going backward. We're going backward. So so that's the what we say. So here, what we did here is is a backward containment. So for the forward containment, I don't think it should be too different. For the forward containment, it should be too different. Okay, so starting from that, Fn is Cauchy, Fn is convergent and hence Cauchy. You can pretty much redo this business. So let's write things down nicely. All right, so actually, because these are all equivalents, you see, these are all equivalents. You can actually, you may move things down a little bit. This process works in both directions to save us some writing, because that's a lot of writing. Okay, here. I'm gonna put it this way. So these are all if and only if statement. These are all if and only if statement. Every step, the transformation is equivalent. Okay, so assume x is in the set on the right hand side. Assume x is in the set on the right hand side. We claim that f of x is Cauchy, and this is what we just proved. And the other direction says assume f is Cauchy, fnx of Cauchy. The forward containment gives a general fact. So that's nice, exactly. I think if we manage to understand this, we were finally able to understand the thought process of showing this. The limit of S measurable function is measurable. So it's all about unpacking the definition of this limit statement, but this case using the epsilon delta definition. Okay, anyway. All right, so now let's see. So here you have, assuming fn of x converges, okay. You have fn of x is Cauchy. Okay. Cauchy criteria. Fn of x is Cauchy. All right. So we need to go from Cauchiness to star. If we can get to star, then we're done. So it suffices to cats are fighting. So anyway, suffices to show star, because star is equivalent to this monstrosity here. Okay? Suffices to show star, and I don't think it should be too difficult. Because we can do something like this. Right. So fn is Cauchy. Let's write down the definition. For every epsilon greater than 0, there exists a big N. There exists a big N such that little n and m greater or equal to big N implies fn of x minus fm of x, absolute value less than epsilon. So we have that. And now we're going to specialize our epsilon to be what? Okay, let little n, because for star, as you show star, you need a for all quantifier. So for all quantifier, you start with by letting little n in big N. Good morning. Good morning. So Tep, you speak Russian, right? So I remember you correcting me a lot, which I'm very thankful of. We'll continue to do the Russian stream next morning, because right now you see is 10 p.m. So yeah. Anyway, so here you have the little n in big N. Try to use that for this definition. So we can say so you're specializing epsilon to be 1 over n. There exists big N in the set of natural so that little n and little m greater or equal to big N implies, no, I can't use n anymore because n is now fixed. So let's say k. Let's use the letter k. I mean, I don't want to use k because k is also occupied. Let's use L. Okay, Lm greater or equal to n implies fl of x minus fm of x. Oh, no worries, my pleasure. Thank you very much. So this is less than 1 over n. So I'm specializing epsilon to be 1 over n here. So this is moving closer to here, right? We're moving closer to here. Actually, I'm going to change the notation to be big J. Sorry, not big J, but simply J. There exists a J in big N such that L and M is greater or equal to J. Okay, and now we can specialize and just pick M to be J. Picking M to be J. Lovely, when the same problem as the programming pops up in math, choosing a name for a variable. Yes. Yes. You spend a lot of time in programming choosing the name of a variable as well. Anyway, so here this will imply that this implies thus L greater or equal to J. L greater or equal to, actually let's just say K greater or equal to J. K greater or equal to J implies Fk of x minus Fj of x. Absolute value less than 1 over n. So basically we're done. So basically, see here in star, this is star. Okay, let me put that down and compare. So yeah. So here we have this. What we want to show is star. So for all n in big N correspond to let n in big N, the existence of J is guaranteed. Okay, and for all k greater or equal to J, you have this. Exactly what we wanted. Exactly what. So we're done here. We're done here. Okay, so I think we should be pretty satisfied with part A now. It uses the Cauchy criteria. That's the key. Okay, part B. Suppose you have a measurable space. Okay, so far earlier you have nothing related to do with measurability and whatnot. This is simply an exercise in Cauchy criteria. Okay. Suppose x and s is a measurable space, and you have f1 all the way to f2 is a sequence of s measurable function from x to r. Okay, and I want to show this is a measurable subset. That's already done, no? That's already done because, I mean, each of them is S measurable. So for all k and j, fj minus fk is S measurable. And minus 1 over n to 1 over n is a Borel set. So this is in S, and we're done. So B is immediate. B is immediate. Once you have A, B is immediate, just like in the proof for this theorem. Actually, you know what? We will redo the proof of this because we were able to follow the proof, but wasn't quite able to decode this. Okay, so we will finish the proof real quick, and I'll come back to 2.48 because last time we spent quite some time trying to interpret this from a lim-sup, lim-inf perspective. Lim-sup, lim-inf, which, I mean, in itself is a nice review. It's a nice review because this turns out to be lim-inf, actually. This turned out to be lim-inf, but anyway, it turns out to be not so relevant to the proof of this theorem. Okay. Lim-inf, lim-sup will come up later. Don't worry, we didn't waste our time. So, I mean, this exercise, I think, is particularly instructive to see how this sort of seemingly intimidating construction is done. So let me just finish up the B real quick, part B. Since for all jk, fj minus fk is measurable, is as measurable. Then the inverse image, fj minus fk, of the open interval 1 minus 1 over n and 1 over n, this is measurable. Oh, not measurable, but rather in S. I mean, same thing. In S for all n. Okay, and now it's done. It's immediate because this is just a countable union, a countable intersection, and we're done. Use the fact that S is closed under countable union and countable intersection. All right. So that's it. That's the end of this exercise. So now let's come back. Let's revisit this big theorem, which is very useful, by the way, um, and a great indication that we're going in the right direction. Because, as we said earlier, I mean, way earlier, countable onion. Hi, Leo. Welcome. So welcome back. All right. I didn't know you were there the whole time, but anyway, here the limit of a S measurable function is still measurable. So to show this, let me just copy this down. How do we get to this weird looking construction, right? That's the whole difficulty. Because once it's shown, everything else is straightforward. So we're assuming that the sequence is pointwise convergent. So we're assuming that the sequence is pointwise convergent, assuming that the pointwise limit is this thing, right? So is f of x. So we want to show that the limit function is as measurable. Revisit this theorem. So perhaps now the proof in Axler does not look so mysterious anymore. Okay. All right. So the idea is, so this is our scratch work. By the way, since this channel is mainly applied math channel, I'm curious what you're learning meta theory for. Yeah, okay. Once again, I hate to always bring up my own ideology, but I don't believe there's an artificial distinction between pure and applied math. You know, as measure theory is a fundamental part, like it's a fundamental part of analysis. And what we do so much on the channel, like probability and stats, like if you ever wanted to see like a rigorous stochastic calculus series on the channel, mastering this stuff is like you need to master arithmetic for calculus. And of course, stochastic calculus is applied in so many areas. Right. So you don't see going through the Earth? No, I don't. No, I don't. This is man-made. It's like the borders between two countries is man-made. The Earth doesn't care. Okay, mass doesn't care. As a subject, mass doesn't care whether it's pure or applied. There is no theorem, and this is due to, if I do say so myself, this is due to myself. There is no way, okay, okay, there is no partition on mathematics of pure and applied. This is just a sociological distinction. Okay. Okay. Anyway, yeah. So because actually, if you think about it, applied math actually requires more rigor. In pure math, you need the formal rigor. Okay, you need to check whether your definition is self-contradictory, whether a conclusion really follows from a premise. That's formal rigor. In applied math, you have to actually consider, okay, whether this beautiful theory from pure math actually is appropriate to reality. So there is some modeling rigor involved, right? So for that, all that matters, applied math need more, if not less rigor. So if you can't play the game that pure mathematicians are already playing, then I don't think you're going to be very good at applied works either. So this is there's no reason to separate. So okay, this is measure theory, that's pure math stuff. I don't think that's a valid argument at all. So anyway, so the scratch work here is done under. So what do we want? We want the criteria for we want 2.39 hypothesis, basically. We want a 2.39 hypothesis, that is for every a in big R, f inverse of a to infinity is in big S. All right, so this is what we want. And so now let's take a look at this. So let's say x is in f inverse of a infinity. What does that say? Well, this is the same as saying f of x is greater than a. F of x is greater than a because the limit, so you see the limit is now greater than a. The limit of k to infinity, fk of x, is greater than a. So that's greater than a. So what does that say? Right, think about what does that say? Can we unpack this using the epsilon delta definition? I hope so. Right, so think about, let's say, this is the same as saying f, the limit, okay, the limit of k goes to infinity, fk of x minus a is greater than 0. Oh, that's my cat. So that's greater than 0. So this is a positive number. So it has to be greater than some. Okay, so this has to, there must exist, you know, there must exist a j. Just pull this to the side. There must exist a j in big N such that, all right, such that the limit of k goes to infinity, fk of x minus a is greater than 1 over j. This is what we wanted. All right, so this is what we wanted. So now let's use the, hold on a second. Now let's get the definition rolling. Definition of the limit rolling. Perhaps drawing a picture also helps. Okay, so x is now fixed, so that's not, no need to visualize that. So here you have the k as an index, and this is a, so to say. Actually, you know what? Actually, I'm just gonna use. I'm not gonna bother with this step. Okay, I'm not gonna bother with this step. You just write f of x minus f limit of f of x is greater than a plus 1 over j. Right, so that's what we're doing here. Draw a picture. Draw a picture. So this is a. Okay, this horizontal line right here is a. And it says there exists some j. Okay, let's just say, okay, this is a plus 1 over j. This is a plus 1 over j. And as k tends to infinity, fk of x goes beyond that. Goes beyond that as well. All right. So when k, yeah, so like this. These are the points. K is uh, k is right here. So this call is k star. Okay, greater than k star. Everything above is greater than a plus j. Okay. Uh, okay. So how do we unpack this? I want to get rid of the limit sign and use everything in terms of quantifier, because quantifiers can be readily converted to set notation, to set to infinite intersection, infinite union, that sort of stuff. So this would mean there exists a k star, or m, say m. Let's call it m. This will mean there exists an m. Say on the picture here, it means there would exist an m in the set of natural numbers such that for all k greater or equal to m, this picture right here, you have fk of x greater than a plus 1 over j. So now everything is in quantifier. You can convert this into set notation. So final step. There exists j in big N. There exists m in big M. In big N, all right. Okay, so I think we're very, very close to a natural construction. So next time when we see this kind of problem, we can do this ourselves. So x is in. Right? So this just means x is in f inverse k a to 1 over j, a plus 1 over j to infinity. Yeah, set algebra with quantifier, quite a classic analysis classic. Oh, Leo, you're uploading a video? That's awesome. I'll check this out soon. Before I go to sleep, I guess. Hopefully that will be done after I finish the stream. Okay, so now it's just a matter of repackaging this into set notation. You see, exist j in big N, exist m in big N. For all k greater or equal to m, x is in this. So this means x is in. Okay? This means x is in the intersection of k greater or equal to m. So k from m to infinity, f inverse of k a plus 1 over j to infinity. And now because both up front, here you just have existential quantifiers, so you just use infinite union. They'll do the trick. So x is now in the infinite union, j from 1 to infinity, union m from 1 to infinity, and then intersection, k from m to infinity. A plus 1 over j, infinity. And guess what? That's exactly the proof. That's exactly the proof. So I think this is very fruitful. Even though we just saw one exercise, this is very fruitful. So remember in Axler, the theorem 2.48 gives this equation right from the start, and we just verify this identity. Of course, that's the way to formally write proofs. Right? You claim something and then you verify it. But well, as people who learn this stuff, this looks very intimidating. And it doesn't seem to be very clear where this comes from. And now we just constructed this identity from scratch. Isn't that nicer? So even though what's in the book is perhaps easier to verify, but if you're not given any hint, now we can do this from scratch. So I think it's fair that we can appreciate how this is done. Right. So we want the hypothesis of 2.39. So we want the F inverse of A to infinity be in this set. So let's just take a look at what this inverse image looks like. And now just a bunch of equivalence deduction. And now finally you get, just to wrap this up, right? This is the inverse image of open intervals of Fk, under Fk. Wish YouTube has a better way to apply specific messages. Yeah. No worries, Leo. Thank you very much. Bye now. Looking forward to your video. All right. So yeah, I think this is very fruitful, actually. This is exactly what's constructed in Axra, and now we know where this comes from. Okay, we don't just verify this anymore. We know actually how you obtain this sort of construction. All right, so I think I'm happy about that. So why don't we wrap this up with another exercise, which is 27. Because 27 is a direct generalization of 2.39. A little bit of a generalization, okay, not that intense, but still, I think it is quite nice. All right, so anyway, there's so many exercises, man, and they're all nice. You can all get something out of it. So anyway, 27. We'll do this until 12. We can do this until 12. Hopefully I can solve this in half an hour, and then we can do some new stuff. Okay, right now, this is what we have for the next exercise. All right, so you have a measurable space, xs, and you have a function from x to extended real. Right? So we want to show that the function is measurable. This function is immeasurable if this condition holds. That is to say, f inverse of a to infinity. Actually, prove or give a counterexample. Actually, this is not a proof. This is not a proof question. We need to see if there's any counterexample for that. If this is true, then f is a measurable function. Actually, you know what? We have a theorem. We have a theorem in the text that says something similar. The proof of the result above is left to the reader. Also see exercise 27 in this section. Okay, so just put these two side by side here. Okay, let's just put these two side by side. I think that's the most instructive way to see this. 27, 27. So we want to prove this theorem. Okay, we know. I mean, well, this is asked to be proved, right? But here, you notice the subtle difference here. In the theorem, we says f inverse of a to infinity closed. But here you have f inverse to a to infinity open. So probably this is false. So probably the answer to 27 is false, but we need a counterexample for that. Okay. Let's see which one is easier, the proof of 2.52 or the 27. Any idea, chat? Which one I should do first? Proof of 2.52 or or exercise 27. You know what? Me personally, I gravitate towards proving 2.52 first, because at least I know this is true. Well, I was told by Axler this is true, so I have greater confidence in proving that's true. But I don't know whether 27 is true or not. So I might be searching for a proof or a counterexample in vain. Okay. Just from a time management perspective, let's prove 2.52. Yeah, I guess 2.52. Thanks. This is what I was thinking. So proof of 2.52. So let's go. And by the way, we need to recall the definition of a measurable function as measurable function when the domain is extended real. Okay, so let's briefly take a look at that right here. I mean, it's the same idea. You take a real set in the extended real, you want the inverse image to be in S. Sure. Thank you, Lockheed, for stopping by. No. Anyway, so here you have the measurable function. It's the same definition almost, but so it hinges on the definition of a real set in the extended real, which is here. A subset of the extended real is called real. It's called a real set if its intersection with R is a real set. In other words, a set C as a subset of the extended real is a real set if and only if there exists a real set B in regular R, not extended R, such that C equals B, or C could be the union of B with could be B plus two extra symbol, plus infinity or minus infinity. So that's pretty straightforward. Right, so that's the all the possibilities for real sets in the extended real. Okay, so for that, I guess you need to check the special cases for the 4 cases, right? But 4 cases. So let's say if you just follow this definition, I mean, to show 2.52, you have no other means other than the definition. So let's put them side by side. Let's write these definitions down ourselves. But definition. So first you have C is a subset of the extended real minus infinity to infinity is real if C is one of the following: C equals B, C equals B, C equals B, C equals, let's say C equals B, B union minus infinity, B union infinity, B union minus infinity and positive infinity. Now, if this is true for some B in the real set of R. All right, so that's the definition of the real set in extended real, and also you have the definition of S measurable function. So X and S is a measurable space. Okay, this is a measurable space. F is from X to the extended real is called S measurable if for every C as a subset of minus infinity to infinity, extended real is real. For every C is real, F inverse of C is real. Not real, is in S. So that's what we wanted. So that's the definition. So to prove 2.52, you can only use this definition. Okay, so let's do that by giving ourselves a real measurable set C. Let C as a subset of minus infinity to infinity be real. Okay, we need to show f inverse of C is in scripted S. So that's what we want. And now you have four possibilities. I have four possibilities. So case, we consider four cases. Four cases, all right? So case one, you have C equals B for some B in the Briel set of R, regular R. Regular R, all right. So we have this condition right here. We have this condition. So, oh, sorry, here we have this condition: minus infinity to A. C is a Briel set. C is a Briel set. Here B is in Briel. Well, I guess you can use 2.39. No, you can use 2.39. No. So first of all, I guess you can say this. You can say this. So hang on a second. Actually, before we even start with this, let's start with analyzing the hypothesis. So note that a to infinity, this is A, Borel, not Borel. Okay, okay, sorry, even though I'm Canadian, I don't speak French. So, Borel, okay, I'll pronounce it the right way. So Borel from the set A to infinity is A to infinity union infinity. And this is Borel in the extended real. This is in the extended real. So given the hypothesis, we have, can we just say that, because there's this property of the inverse function, the inverse image, and also the inverse of A to infinity is the inverse of A to infinity open and then union F inverse of this. Is this identity helpful? Right, we assume that F has this property. This is in S. Okay. For all A in R. We want to show that for every C that is Borel, F inverse C is in S. Is that helpful? Um, A to infinity. I'm saying, can we consider four cases? Okay, I don't know how this can be helpful, but let's take a look at the four cases here. If C is just B, this is like a regular Borel set, right? It's just C equals B. It's a regular Borel set. So we have the hypothesis. We have the hypothesis. So um, the hypothesis says this is always in S. This is always in S. So we want F inverse of C to be in S. I guess you would like to approximate C, or at least approximate B, using countable unions, countable intersection, all that shenanigans. Why don't we revisit the proof of 2.39? Because I remember that to be quite tricky as well. 2.39 here. Even though we verified the proof, it was still hard. 2.39 says x has a measurable space. F from x to r is a function that has this property. It's just very similar to what we're trying to prove here. And this is true for all a. Then f is S measurable. Okay, and here's the proof, which I didn't write in my own words. Perhaps that's the reason I was so rusty today. But basically, here we wanted to show that the collection T of sets in R, of sets A in R, such that F inverse of A belongs to S, is a sigma algebra. Okay, so here let descriptive T to be A as a subset of R, such that F inverse of A is in S. We want to show that every Borel set of R, subset of R, is in T. Hang on a second. Hold on. Hold on. So here A doesn't have to be Borel. In the collection T, A doesn't have to be Borel. T consists of elements or sets of R, sets in R, such that the preimage of A is in S. If you can show every Borel subset of R is in T, that means for every Borel subset, say A, its inverse image is in S. Then you're done. Okay. So, and here's a clever trick. To do this, we show that T is a sigma algebra. Why is that useful? Because the collection of Borel subset is a sigma algebra itself, the Borel sigma algebra. And T contains the set. By the hypothesis, T contains the set, the classes of set A to infinity. So T has to be at least as large as the sigma algebra, as the smallest sigma algebra, okay, containing this class. Here, T, if we can take, okay, let's verify this later, but if you know that T is a sigma algebra and T contains this class of subsets, then T would be at least as large as the smallest sigma algebra contains this class of subset. Okay, um, and um, and from that you would know that T contains every open set. Okay, from this you can show that T contains every open subset of R. So now T is a sigma algebra that contains every open subset of R. Therefore, T is as least is at least as large as the sigma algebra that contains every open subset of R, which just happens to be the Borel sigma algebra. So T contains the Borel sigma algebra, and we're done. So that's the overarching idea here. So I guess we can follow this template and write down the strategy for 2.52. So let's do that. So here, to prove the general idea of the idea of proving 2.52. Let's formulate the process here. Okay, so once again, let's going to define T, scripted T, to be the collection of sets A, which are subsets of the extended real minus infinity to infinity, so that F inverse of A is contained in S. Sorry, not contained, but is a member of S. So that's what we wanted. Right. So this is what we wanted, and we want something else. Okay, so we want the what's going on here? We want to show this is we want to show the Borel sigma algebra over the extended real minus infinity to infinity is contained in scripted T. In scripted T, all right. So to do that, we can show T is to do so. To do so, we do the following. Okay, one, show T is a sigma algebra. Okay, show T is a sigma algebra, and second, you need to show T contains all hold on a second. Show T is a sigma algebra, and you want to show that T contains all open sets in the extended real. T contains all. And by the way, what are open sets in the extended real? What should we say? K contains all sets of the form. Say U union with infinity, U union with minus infinity, U union with plus or minus infinity, for some open set, for some regular open set, okay? For open U in R. So that after that you will be finished. So that's the idea. And now let's proceed with that purpose. Okay, so anyway, let's just remove all of this. So starting with this construction T. T is the collection of subsets in the extended real such that the inverse is contained in S. The inverse of A is contained in S. Okay, all right. So we want to show that T is a sigma algebra. Okay, define scripted T is A, set of A such that A is contained in minus infinity to infinity is a subset of extended real such that F inverse of A is in scripted S. All right, so that's what we wanted. So we claim, so 1, T is a sigma algebra. Okay. Let's do that. T is a sigma algebra. You need to check the sigma algebra axioms. 1, does it contain the whole set? So does, say, minus infinity to infinity itself is in there? Here, that's the assumption, right? Is minus infinity to infinity itself in there? But the thing is, if you let A, starting from this assumption, you want to show, I'm saying is you want to show minus infinity to infinity, the whole extended real is an element of T. So for that, you need F inverse of the extended real to be in S. Actually, that's certainly true. That's always true. Because this is true because F inverse, this is trivial, minus infinity to infinity, because F is from X to minus infinity to infinity. This is just big X itself, which of course is a member of the sigma algebra. So, simple. Second, close under countable, what's that, countable, not countable, but just complement, close under complement. So you let, say, let A be in, hang on a second. Yeah, let A be in scripted T. You need the complement. You need the complement need to show minus infinity to infinity set minus A is also in T. Why am I using scripted letters? No, just regular print letter A is in scripted T. So we want that. That's closed under complement. All right. So starting from the definition, well, F inverse of A is in S. So since F inverse of A is in S, F inverse of A is in S, the here F inverse, the F inverse of minus infinity to infinity minus A, use the set difference property, which would be F inverse of minus infinity to infinity set minus f inverse of A, which would just be x minus the f inverse of A. This is in S, since S is a sigma algebra. Fa is in S, the complement of Fa is in S. So we're done here. The third one, all right, so countable union, that's also very easy to show because you just use the inverse function property, inverse image property. So let A1, A2, dot, dot, dot be in scripted T, okay? And we want to need to show the complement, not the complement, the countable union, n from 1 to infinity is in scripted T. So we want to do that. Okay, so, well, this is easy because f inverse of the union is just the union of inverse images. Very nice property of the inverse image, help us out here. Okay, so yeah, each f inverse of an is in S, so the countable union must be in S as well. So we're done. So T is a sigma algebra is really easy to show. And now we need to show that T contains all the sets of this form. Okay, so T, let's say we need to show, okay, let U, okay, to do that, let U be open. Let's say, actually, then you know what? Let C be in the, let C be in minus infinity to infinity, such that C has the following form. Such that C has the following form. Actually, you know what? Let's write it as this way. So C, let C be one of the following. Be of one of the following forms. So C is equals B. C is B union minus infinity to infinity. Actually, sorry, my bad. I was saying it should be U, open set, not a general but real set. Okay, U union plus infinity and U union plus or minus infinity. Following forms. For some, U in regular R open, C equals this. So we want that. Okay, sorry, not we want that. Let C be one of the following form. We need to show the inverse image. No. Yeah, we need to show the inverse image of C is in S, i.e. C belongs to T. Same thing. Okay, so let's do that. So can we do that? Well, we got to use the hypothesis somehow. We still haven't used the hypothesis, okay? So even though 1 is pretty nice, we never used the hypothesis, so we have to use that in the... Okay, so let's check out 2.39 again. Yeah, so by the hypothesis, it contains a to infinity for all a and r. Okay, so here we just need to show that T contains all the open intervals in the 2.39. But here, what we want is, okay, by the hypothesis, first of all, by the hypothesis, f inverse of a to infinity closed, okay, a to infinity closed, this is in S for all a in real. So we have that, i.e. T contains the class of sets a to infinity, left open, right closed, such that a is in real. Okay? So how do we show that? Actually, what do we want? What do we want? Yeah, okay. U is open. U is open, all right? I guess you can use these sets to approximate, I guess you can use these sets to approximate, let me just check this again. So it's under complementation, you also have this. If we use, okay, let's just follow this and see what we can do here. Okay, let me, actually I'll put it on the other screen and I'll repeat what Axler did and adapt to our setup. So, therefore, by complementation, here by complementation, minus infinity closed to b closed is a complementation of this form. Right, b in real. In real is contained in T. Complementation. So we have that. All right. Okay, so, well, and now you can take the intersection of the two. Now take the intersection so you get a set of the form A to B, left open, right closed, A less than B, AB in real, is in T. So this is the intersection. Because T is sigma algebra, they're all in T. Okay, and now what we have here, so we have this conclusion that any open interval can be approximated by this. Any open interval can be approximated by this form. So that is to say, here, A to B can be seen as a countable union of k from 1 to infinity, a b minus 1 over k, closed here. Okay, this is in scripted T for all AB. Okay, and another shape. So we have, I mean, here you can see a to infinity. This is what a to infinity union infinity looks like. And for, I want the other possibility, namely minus infinity to b. I want the minus infinity to b to be also here, closed, open. I want this to be also in T. Can we do that? I think we can. You can use what's that? Use approximation of this set. This is minus infinity. So let me see. So here you want, this is minus infinity and this is b. So you want, let's say, b to be slightly less than 1 over k. And then it has to be open up, yeah, closed here. Question, is this off topic, but for some reason I love watching people break down math, even though I don't understand it. Yeah, like, so, on bonds, which is full of math, okay. You mean financial math? Thank you very much. Thank you very much. Actually, if you don't understand something, like, and if you want to understand, like, let me know. I can stop at any moment. Okay. So yeah, I said earlier I'm just doing it for myself, but well, if you do ask question and you want to go back from the beginning, I will stop my thought process, okay, and explain to whatever degree necessary, okay. Okay, so yeah, this is what we want. This is what we want. So this is a union from k to 1 to k from 1 to infinity, because now we're taking the union of set of this form. So this is still in T for all B. Okay, so far what we have, you have the assumption that f inverse of minus a to infinity is in S. Okay, and the a to b, okay, just regular a to b, open interval, and minus infinity to b is in T. Okay, so overall, since the C, or earlier, the C, actually, you know what? They just move it down there because I stated C, defined C to be one of the following, but never bothered to show this, to use this until now. Why don't we just bring it down here? So what's the point of 2? The point of 2 is to show that all open sets union plus or minus infinity is in T. Okay, here that's the T contains all sets of the form. All sets of the form here. U union minus infinity, U plus union infinity of the consent of the form, where U is open in R. So this is our second objective. So here we have 3 key results. So I mean, not results, but statement. First, this is the hypothesis. First, this is a hypothesis. So that is to say, a a to infinity is in T for all a. And then we have a to b open interval to be in A. to be in t, and we have minus infinity to b is in t. So this is what we have so far. And we want to get back to the main objective. This is lagging right now. Let me just delete that. Don't need that. Don't need that. All right. So this is what we have. So how do we connect to our main objective? Well, U is an open set. U is an open set, so it is a countable union of open intervals. Oh, do you always stream like this? Yeah, most of the time. Most of the time. Like if you can check out my past recording, kind of all like this. This is the norm of the channel. I mean, we do sometimes chit chat and whatever, but this is how we typically do things. All right. So basically, at this point, you're pretty much done, because since U since any open set U as a subset of R is a countable union of intervals, of open intervals. Is a countable union of open intervals. I'm saying is so these sets, okay, are all then these sets are all countable unions of sets of the form of sets among in collections in collections A to B and being real. Okay. Union minus infinity to B. B is real. Union A to infinity, A is real. Okay, so that's it. All right, so that's 2. So what do we have here? T is a sigma algebra, and T contains all the Barreal sets. Contains all the Barreal sets in the extended real. So therefore, this is to say that T contains the Barreal sigma algebra from minus infinity to infinity, which is exactly what we wanted, and therefore F is S measurable. So 2.52 is now proved. 2.52 is now proved, and we wanted to see whether 27 is true or false. And I think it's false. So can we give an example that, say, missing the infinite sign is not okay? Where does the infinite sign play a role here? In the proof above, where does the infinite sign play a role? Well, infinite sign plays a role here if let's say if you don't have the infinite sign, if you don't have the infinite sign, then say taking the complement of that would give you minus infinity b union with a positive infinity. Union with a positive infinity. So we want to construct a how do we construct counterexample? So to construct a counterexample, you need to find a Borel set in the extended real. You need to find a Borel set in the extended real so that its inverse image is not in S. So that the inverse image is not in S. Okay. So why don't we look at, say, just a singleton, positive infinity. What's the inverse image of that? So basically, we need to construct here. To provide a counterexample, we need to construct a function that has this property, but it is not measurable. So why don't we just pick a simple example? Say you want S to be as simple as possible. This way, you have a high chance of not including a certain set, right? So you can let S to be just the trivial sigma algebra, just the empty set and the extended real. Okay? And what? So here, let's say f takes two values. Can we do that? F takes two values. So of f of x is, it can't be infinite. It can be infinite if x is 0. Say when x is 0, f of x is infinite. When x is non-zero, and x is non-zero, then f is 0, so to say. Okay, so let's just give this simple example a try. So let's think about the situation of the inverse image. So A is an arbitrary real. If A is greater than 0, if A is greater than 0, then you have just a positive number, but does not include infinity. So that's an empty set. So let's say if A is positive, actually A can be 0 as well. So let's say A is greater or equal to 0. Then the inverse image of A to infinity would just be the empty set. I mean, that's okay. The empty set is in S, so that doesn't violate the assumption. And what about the situation where A is less than 0? If A is less than 0, then what? If A is less than 0, then the inverse image would contain every x it's set except x equals 0. But that violates the assumption. That's not okay. So this is not a valid counterexample. What if f of x equals infinity everywhere, huh? For all x. It's even more extreme. So for every a in big R, this is the empty set. This is the empty set. But So it's the empty set. So this assumption is now satisfied. But is f measurable? Well, the singleton infinity, that's for real. Because that's just the empty set union infinity. So that's for real. And the inverse image for that would be big X. So there's no contradiction. So there's no contradiction there, and I don't like that. We need a contradiction. We need a contradiction. Okay, so this is complicated, huh? So I wanted to construct a counterexample. I mean, it must have some funny business with the with the positive infinite sign. So it needs to contain the empty set X itself, but it can't be f of x equals constant infinite, because if that's the case, the inverse image of infinite would just be big X. There's no contradiction. So I want the inverse image of infinite to be not in S. I want to cook up that. How do you? That's why I wanted like a zero. Okay, f of x equals infinity if x is non-zero. If x is zero, then it's, or actually it should be the other way around, huh? Actually, you know what? Let's try this way. If x is non-zero, it's just infinity. And if x is zero, then it's, say, minus infinity. Can we do that? Actually, so I'm not quite sure where am I going, but let's just try some more random example. Let's say when x is greater than 0 is positive infinity, when x is less than 0, or why do I keep dealing with functions of a real number? You don't have to do that. Here x is an arbitrary set. Here's an x as an arbitrary set, so let's see the following, if the following works. So I'm setting S to be the trivial sigma algebra. I'm setting S to be the trivial sigma algebra so that it contains as few sets as possible. And I want f inverse of infinity to be not in there. So it can't be empty, or it can't be the full set either. It can't be the full set either. So can we say f of x is infinite only at one point, and everywhere else is constant? So that was the original motivation. F of x is infinite when x is 0, and when x is non-zero, it's just 0 everywhere. And that doesn't work. That doesn't work because, say, because of the hypothesis, f inverse of minus 1 to infinity. This would include, so the inverse image of that, f inverse of f inverse of minus 1 to infinity would be minus infinity to infinity. Minus infinity to infinity except 0. So except 0. Except 0. And because of S is a sigma algebra, it needs to be closed under complement, so it would automatically include 0. And I don't want 0 to be in there. I don't want 0 to be in S. This way, I can cook up a non-measurable function. But this doesn't work. This does not work. Okay, so I want f proof of give a counterexample. If there's anything, is there anything that the proof would break down if I only assume a to infinity open? Here, I use the hypothesis. So by the hypothesis, you would have a to infinity instead of a close sign on the right. Okay, if you only assume f inverse of a to infinity open is in S, then you would have this, something like this. And by taking the complement, you would have this extra union infinity on the right. T would include sets of this form: minus infinity to b, minus infinity to b, and with the union of infinity. With the union of infinity. My goodness, I feel fucking stupid. I mean, it feels like there's got to be something funny you should do with a positive infinity sign, but I don't know how to construct a function f, man. And what else do we need here? And is there anything else that gives us funny business? Because here, once you take the intersection, there's other infinity just dangling on the right. If you take the intersection, if you take the intersection, actually not intersection would not include this. Intersection still looks okay. This is still what we have here. So T would include set of this form, minus infinity to b, with a positive infinity dangling on the right. And eventually, our goal is to show that if the Barreal sets in the extended reals are all in T, then we're done. So T includes, hold on a second. What does T include in this case? You only have an open on the right. It won't include a to infinity, right? It won't simply won't include that. It won't include that. It just you're never gonna get a positive infinity with a closed set on the right. You're never gonna get that. But in the definition of the measurable function in from x to extended real, you need for all Barreal sets C in the extended real f inverse of C to be in S, which include the set of this form a to infinity with a closed sign on the right, square bracket on the right. So you should have that, right? So this is what is needed for a function to be measurable. But here we don't guarantee it. just erase what's, so we don't guarantee that. Why don't we do something, once again, the counterexample should be right in our face. X, let's just say, it only takes two values, a, b, and so the subsets of X are easily attainable. So the subsets of X are just empty A, B, and AB. Because for this simple situation, the sigma algebra only has two cases, either the trivial or the power set. You can't just say, there's nothing in the middle. So that wouldn't be okay. That wouldn't give us a counterexample. So what about three elements, huh? What about three elements? So you got empty, you got the full set, singletons ABC, singletons ABC, and the two element set AB, AC, and BC. So you have that. You have that. Well, what do you do here? How do we construct a non-trivial sigma algebra from this? You must have empty and the full set. Say you only want A. Let's say you only want A. Then you just need BC. Okay, so let's do that. So let X be the three element set, and S is empty ABC. I'll just say X empty big X singleton A and BC. This way you make sure it's closed under complement. This is closed under complement and closed under union. So it's all good here. It's all good here. So what is not in X? What is not in S? Well, the singleton B, for example, is not in S. Singleton B is not in S. So I want say minus infinity to minus infinity of the set singleton infinity. I want that to be not in S to create a counterexample. I want this to be not in S. So why don't we just call that B? Okay, why don't we just call that B? So this just means that FB is infinite. FB is infinite. All right. So this is non-measurable. Okay, so this is non-measurable from the get-go. X is this set, S is the sigma algebra, and I define FB to be infinite. I still need FA and FC, the value of FA, FC, to complete the definition of a function. I still need FA and FC. They can't be infinite, otherwise, well, they can't be infinite because I want FB to be infinity. I want F inverse of B to be the singleton B, so that it's not in here. So FA is, let's say, FA is what? Actually, you know what? FB is infinity, and okay. Can A and C equals 0 then? Does that work? So let's say A and C are 0. pretty random, but let's see if it works. So first of all, is this still non-measurable? I still want this to be non-measurable. Still want this to be non-measurable. So let's say, yeah, this is still, because of this is still non-measurable. This is still non-measurable, that's good, that's what we wanted. Does this satisfy the hypothesis though? Is it true that for every A in real, is it true that for every A in real, F, no, you can't use A, but let's use Y. Why don't we use Y? For every Y in real, F inverse of Y to infinity, F inverse of Y to infinity is F inverse of Y to infinity is in S. So if Y is greater or equal to 0, what's inverse? What's F inverse of Y to infinity? If Y is greater or equal to 0, well, everything is positive. Nothing equals positive here. Nothing equals positive yet finite number. So this is just empty, which is okay. It satisfies the hypothesis. And if Y is less than 0, then what happens? If Y is less than 0, then F inverse of it would contain, so that's the thing, if Y is less than 0, then say Y to infinity would contain A and C. It would contain A and C. If Y is less than 0, then Y to infinity will contain points A and C. But A and C is not here. If A and C is not here, A and C is not, so it violates the assumptions. This is not a valid counterexample. But if you do add A and C in the set S, then we automatically include B, which destroys this crucial criteria that I wanted to use. So at this point, I'm starting to think there might not be a counterexample at all. I think this might be true, actually. 27 might be actually be true. Because, I mean, we're running out of time here because I want to finish this at 12 o'clock. Let's just, once again, look for AI for help. Okay, so, okay. I'll be back in like 2 minutes. Um, Sorry, guys. Um, I need to give medication to my cat. She has allergy, unfortunately. Yeah, I'm still trying to feed her some medication, which she doesn't like. Mm, almost ready. Okay, so here, we're interested in this question. So say true or false. Let's say if x and s, scripted s, is a measurable space. If this is a measurable space and f from big X to extended real is is a function so that f inverse of the set A to infinity open in scripted S this is true for every A, for all A in big R. Okay, in big R, then f is S measurable. Okay. Actually, this is true. Um, how do you go for? Well, I mean, well, you just do it. What else can I say? I guess I mean you have desires to make progress, and then you just do whatever it takes. It's needed. Okay, just it's all about having the right expectation. I know the subject matter is hard, so I don't feel bad if I get stuck in whatever. So assume this is true. Assume this is I think yeah. Assume this it suffices to show that the preimage of every open set of R belongs to S. Yeah. So you have an open interval. Yeah. So that's we know the first set is measurable, yes, and now I need to show that the second is measurable. So you get that. Actually, it doesn't matter. The right endpoints simply don't matter. So let's say it doesn't matter if say f inverse say the f inverse of a to infinity closed is not in S. The answer is no, it doesn't matter. The issue is that f takes values on an extended real while the hypothesis only involves only involves this. Let's see why this is sufficient. So I was unable to cook up Counterexample. Do you think measure theory is required to learn stochastic? Yes, absolutely, absolutely. I mean, it. So actually, you know what? Sorry, Flobby. Do you think measure theory is required? I think you can get a reasonable working knowledge of how stochastic calculus work without measure theory. You can get the main intuition for that. However, because of most books on measures on stochastic calculus written in measure theory, it will be very difficult if you don't know the measure theory. So it's like if you don't measure theory, you always need somebody else to translate that for you or water it down for you. Okay, you lack the ability to do independent inquiries. That's the issue. Right. So stochastic calculus, do not treat this as an absolute barrier. It's like, oh, stochastic calculus is completely undoable if you don't know any measure theory. That's not true. But you lack the independent capability to learn it. You always rely on somebody to translate it into or water it down to some special case for you. So that's the problem, in my opinion. I mean, it's not a debilitating problem. You can still say gain a great deal out of it. Okay? But for a serious study of stochastic calculus, I don't think there's any. I mean, it's not opinion. Okay, it's just there's no other way around. Okay, so here it says I was saying, like, I was asking AI, like, what if it does it matter? The right endpoint doesn't matter. I think this is false. Okay, so I mean, yeah, I want the debate to go on because I want the debate to so to say to clarify the issue, because I was convinced that this is wrong. Because if that's true, why don't we weaken the theorem? Okay, question: if x is 0 and 1, then S is a trivial sigma field. F0 is infinity. Yeah, the problem is never about, the problem is not you cannot construct a non-measurable function. The problem is you need to still satisfy this, and f is non-measurable. Let's try out your example. HYZ, let's work this out. So x is the set 0, 1. Okay, and S is trivial sigma algebra field. So sigma algebra or sigma field, same thing. S is 0 and x. Okay, and you let f of 0 to be infinity, and f of 1 to be minus infinity. Okay, and yes, it is true that f inverse of infinity singleton, okay, is 0. This is certainly true. But think about the other hypothesis. It needs to be f inverse of a into infinity is an S for every a in R. F inverse of say, all right, a to infinity. So because a is real, it will never be minus infinity either, right? So this is always empty set. Is that always empty set? For every a? Now let me check. So this is f of, someone stopped it and use relentless. Anyway, yeah, so HYZ is saying f inverse of a to infinity is empty for every a in R. So you let f of 1 to be minus infinity. You let f of 1 to be minus infinity so that a to infinity, a to infinity will never contain any actual value of the function. So the preimage is always empty set. Is AI just BSing me right now? And then what is this so-called proof? My God. Assume this is true for every A. Okay. It suffices to show the preimage of every open sub. No. You need to show every open subset of the extended real. Okay, so I think there's something wrong here. Perhaps this is BS. I think this is nonsense, and I think this is an excellent example. So this is minus infinity. So I was saying, like, if you just say it's not, it's quite surprising, isn't it? It's quite surprising is that it's not minus infinity you need to, it's not, let's say, positive infinity that causes the issue. It's minus infinity that causes the issue. Yeah, that's not the same. That's not the same. So I picked a finite value, see? I picked a finite value here. And it didn't work out that way. So yeah, if x is, let's just recheck everything. Okay, so this is certainly a sigma algebra. And this is the function from x to the extended real. And the singleton, this is a Barreal set. This is a Barreal set this is a Barreal set in extended real, I believe. Yeah, this is true. And you have 1 here. And f inverse of a to infinity is empty. Oh, okay. Wow. Amazing. Thank you so much. Thank you so much, man. HYZ. I'll put you in the credit here. So credit HYZ 5. I don't know how else I can express my thank to you, but yeah, this is excellent. This is an excellent counterexample. Because for some reason I didn't think about doing something about the minus infinity. Okay, if I use minus infinity, perhaps also this problem will also be resolved, I guess. If let's say A is minus infinity, B is minus infinity, then yeah, it will also work. It will also work. So suddenly, if you pick 0 to be, so if you pick the other numbers to be minus infinity, this will also work. All right. So yeah, that'll be it. That'll be it. And actually, that will be a good time to stop the stream because it's getting very late. And all right. So yeah, thank you guys. Thank you very much for this joining the stream. And I will see you guys next time. Okay. And the notes, I'll try to compile all the notes in a Google Drive, so people interested can take a look and see for themselves. And hopefully, it's going to be helpful for someone. Anyway, thank you.